I'm Associate Professor Dr. Zuraida Ali, and it is my pleasure to be your MC again, especially for this room. To commence our event today, I would like to invite the chairman for this session, Yang Berbahagia Datuk Insinyur Muhammad Azmi Ismail, the Commissioner for National Water Services Commission, SPAN. Please welcome.
Thank you and terima kasih OMC Dr. Zul. Yang bahagia Datuk Roslan, Chief Operating Officer TNB Power Generation Sdn Berhad. Yang bahagia Datuk Haji Sabani Sohaili, Group Chief Executive Officer Sarawak Energy Berhad. Lieutenant General Engineer Sajad Ghani, retired, Pakistan Water and Power Development Authority, WAPDA. Good morning and Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Azmi, and I feel privileged to have the opportunity to introduce our esteemed keynote speakers who will be sharing their valuable insights and experience related to dam safety. I would like to extend a warm welcome to everyone to the final key session of this conference. It is wonderful to see so many dam experts and professionals gathered together to exchange ideas and insights related to the future in dam safety. And also we are fortunate to have with us an individual who has dedicated their life to advancing this field and has made significant impact in this industry. Before we begin, I would like to take a moment to acknowledge yesterday's keynote session by 5 of our keynote speakers. I think many of you were in attendance, and I hope you found it to be as insightful as I did. It's always great to hear from experts in the field and gain new perspectives on the topic that matter most to us. With that said, let's dive into today's keynote and continue the conversation. The first speaker is Yang Bahagia Datuk Roslan Abdul Rahman, who will be representing on behalf of Datuk Nur Azman Mufti as what in the timetable, in the schedule of speakers. Yang Bahagia Datuk Roslan is a Chief Operating Officer, will be, previously was Vice President of Generation Division prior to the establishment of GENCO. And without further ado, I would like to invite Dr. Roslan to join me on the stage, please.
Bismillahirrahmanirrahim. Thank you, Datuk, for your kind introduction. Distinguished guests, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So today I'll be representing Datuk Nur Azman Mufti, the Managing Director of TNB Power Generation Sdn Berhad, who cannot be here today due to his overseas assignment. And my topic today is about the implementation of dam safety program for Tenaga Nasional Berhad GENCO operated dams. After seeing yesterday's keynote by a few speakers, I come to realize that the issues or the risks or the problems that we are facing is almost similar or the same in general, whether the dams is in Malaysia or in India or Europe, for that matter. And I think this conference is a very good sharing session where we can continue to share our experience in the operation and maintenance of the dams. So today, let me share with you some of the key points on this operation and maintenance of TMB dams, especially very specific manner of how we maintain and operate the dams with regard to the risk factors, the impacts, and as well as the whole management of the dam from the design until retired or continued operation after the expiry of our power purchase agreement with regard to hydroelectric generation. So the outline of my presentation today is I will touch a bit on overview and introduction, the framework of our dam safety program, the challenges in implementation of the dam safety programs, what will be our future planning on dam safety, and the way forward. Next. Okay, basically these are some of the major dams that we are operating and maintain at the moment. And TNB's dams are, the major functions of the dams is to produce the hydroelectric power. Besides the other benefits that we contribute in terms of flood mitigation, water irrigation, and also the water consumption. So the dams are located in few states, in Perak, Pahang, Kelantan, and Terengganu, and it was built at different period or times. With the oldest, I think, probably Chendro in 1930, right? And to the latest of the dam that we built in Ulu Jelai in Pahang and Hulu Terengganu in Terengganu. So the challenge that we have here is that when we built the dam, the design during that time was based on certain assumptions, in terms of the risk factor, what are the variables involved, and so on. But now, as you can see that there are so many changes in the factors that give impact to the dams. I would consider it internal and external factors, control, the things that we are in control and things that we are not in control. It used to be that the dams were built in a very isolated location, and it is free from any external factors. But now you can see that the dams are more and more exposed. People are not coming or live or having the activities nearer to the dams, and it gives the impact to the operations. So we have to manage this risk. We have to mitigate on how to operate or how to live with the new surrounding that we are here. And other factors, I think that is impacting not only us but everybody, is on the climate change. Okay, so we have now a very unpredictable weather. The rains that we receive, is sometimes it is out of the ordinary. Maybe I will share something on what happened in one of our dam in Kenyir, that now that it requires us to review and put the mitigation in place on how we are going to manage or to mitigate the risk, so that it will not give any negative impact to our operations. Next, please. Okay, before that, basically, power generation in the country, at the moment, the total installed capacity in Malaysia is about 28,000 megawatt. And TMB power generation share is about 50% of that. And the hydro generation capacity total is about 2,500 megawatt. So it's less than 10%, but hydro power generation plays a very vital, important role in terms of system stability to provide the power during the peak loading, as well as on the voltage control. Okay, a little bit on our dam safety program and journey. Over the years, we have introduced many programs and initiatives to enhance our dam safety program. And we started, we seriously look into in a very systematic or integrated manner of how to operate the dams from the years from I would say in 2004, Before that, we have some program like the dam safety review, where we carried out this dam safety review in 10 years interval period. So this dam safety review is assessed by third party, consisting of international and local dam experts to look into our dams operation and maintenance, the structures, integrity, and as well as the other external factors, whether it is from downstream, upstream to the downstream's management. And then we also carry out the dam break study. This is in view of what I said just now, in view of the new climate change and so on. And so we have to review the dam break study to see what will be the latest modeling like, and what will be the latest flood hazard map like, so that we can predict what will be the socio-economic impact if something happened to the dam. And then in 2010, we enhanced our emergency response plan. It used to be that we carried out the response plan within our own dams, area, plus the local communities. But ever since what happened in Kenyir in January last year, now we are expanding the program to the state, and we are even planning now to do at a national level, in which it has not yet been materialized. But this is something that I think is very important for everybody now to be aware on the emergency during in the event of there is some event with the dam, so that everybody is prepared. ICBDM is integrated based community-based disaster management. This is a program where we engage our stakeholders, anybody or any stakeholders that have any relations to our operation that have impact to the dams, so that, as I said, there will be more understanding and cooperation from everybody. Because managing the dam is not confined to the operators alone. There are many stakeholders that need to be informed, and they need to be involved, because there are areas that is beyond the operator's control that we need the assistance. And the latest program that we had is the risk-informed decision-making on dam safety. This is still under development. We have started at a few dams, and we will try to complete it in all our dams. So basically, this is to look into our the risk factors, the failure mode analysis, how we identify and assess our risk, how we prioritize or rank the risk, and what will be the action that need to be taken. Okay, next. And we currently, as you know, there's no act to govern the dam management in Malaysia. So we are using at the moment is the Malaysian guidelines, My Dams, and as well as the Majlis Keselamatan Negara on the emergency preparedness. And of course, ICOL and other international reference is always our guide on how we can manage or guide in our operations and maintenance procedures at our dam. Next. Okay, I would like to share the framework of our dam safety program that we are having right now. Can we, next please? Next. Okay, so basically there are 9 key areas that we are managing to ensure that our dams are really managed in a very integrated manner. We look from end to end, and in terms of commitments or undertaking from the top until to the bottom of the whole range of our structure. So there is a safety policy that we already put in place. We conduct the safety review. We look into the operation and maintenance of the dams in terms of procedures. Okay, and then we conduct the dam surveillance, the emergency preparedness that we design together with our stakeholders. We improve on our documentation and information management. And on the competency of the people, we continue to give them training, education, certification, and we look at the process and procedures, as well as the risk assessment. I will try to deliberate it in more detail in the next slide, please. So on the first thing that we do is that we establish the safety policies on the 3rd of January 2022. So the policy is very important to give the undertaking from the top of management that we take the dam safety management in a very serious manner. So the commitment from the managing director himself, and with the policy we outline what will be the standard that we are going to use, and the standards are going to be established or used all across our dams in our system. Okay, next. And the dam safety review, as I mentioned just now, is been carried out by registered professional engineers, by the specialists, both from inside and also foreign, outside the countries. And this dam safety review is carried out for both structural and non-structural areas. We look at the whole dam's safety aspects, and from the report, we use the report to enhance or to close any gaps by the findings of this report. So this is very useful, as I mentioned just now, that with regard to the new factors, the new variables that surface now. Probably the rule has already changed. The factors or the data that we put in maybe 40 years ago now is already no longer valid or relevant, and we have to do the new formulation or sort of calculation on what would be the best design or the improvement that we need to do to improve our dam. Next, please. And the operation and maintenance of the dams, we look into the procedures. We look into our equipment, the instrumentations that is measuring the data, and we look at both civil, mechanical, and as well as the reservoir and also the downstream. So sediment management now is already becoming more and more of a headache to us. We are spending quite some, some of the costs that we have to put up to ensure that our reservoir capacity is being maintained as per the design level. The dam surveillance is carried out every 6 months to gather the data for the team to conduct the analysis, okay? And the instrumentation is very important. It has to be calibrated, because if the instrumentation is not accurate, then we get the wrong reading and the wrong interpretation of the dams. Okay, next. The emergency preparedness, as I mentioned, is something that we take it very seriously. We carried out the drills every year, especially on the high-risk dam, and we engage the authorities, the stakeholders, the major stakeholders like the district office, which chair the local emergency preparedness, okay? The bomba, the firefighters, the police, hospitals, and etc. And we keep on engaging the people through many programs, through many briefings and talks, even at the school level, to let them understand what needs to be done, what are the risks involved when they are living or staying very near to the dams. Okay, next. The documentation and information management is very important, because all this data or the information about the dams has to be properly documented, has to be properly stored, and when you need it, it is to make sure that it is always available, and all those data has to be verified, and put up in one place where it can be accessible to everybody. And from there, all this data is used to carry out the analysis, the risk analysis, and so on. So we make sure that now we have a centralized, in a very structured way of managing our data and information. Okay, next. And of course, training and education. The people has to be competent, okay? And we make sure that we continue to give them trainings to get the proper certifications. Okay, and can we go back to, okay. And I think with the good people, with the people that has enough competencies, then we can make sure that all our procedures or our process is being carried out or executed in the manner that that is outlined in our plan. And of course, the process and procedures has to be there. It has to be enhanced. It has to be reviewed from time to time, so that the procedures is always updated, and it is life that is applied to the current situation. All right, next. The risk assessment, as I mentioned just now, also is very important for us to carry out the risk assessment and to ensure the dam's status is at the level that is acceptable or meet the guidelines of the guidelines that we refer to. So one of the latest program that we have, we are doing right now is a risk-informed decision-making. And the objective of RIDM is to identify on the dams risk. We carry out the analysis, we do the ranking on the risk, we do the qualitative and quantitative analysis, what will be the impact, if things happen, what will be the impact to the dams, and as well as if we need to upgrade or to improve the dams, what will be the cost-benefit analysis that we need to carry out, so that we will make sure that whatever improvement that we do, it is optimized in a manner that it will ensure that the dams is at the very safe level to be operated. Okay, next. Okay, I would like to go to the, is it the next slide? Is it the current slide? Can we go to the previous slide? Okay, all right, okay. The challenges and in the implementation of dam safety program, there are many challenges that we are facing. And these are, as I said, the challenges can be by the internal or external factors. So we need a cooperation of everybody to make sure that we get a very good assistance and we meet our objective in the operation and maintenance of our dams. Can next, please. Okay, on the governance at the moment, okay, our reference is only MyDams as a guideline. There is no act that is governing the dams operation in Malaysia. So, as we know, MyDam is just a guidelines. It does not constitute a design, construction, or operation code of practice. So, but being a responsible dam owner, we are very committed to make sure that as much as possible, we are performing to the international standard. So probably one day, Malaysia will have our own act to govern the standards for all the dam operators in the country. Okay, next. And I think this is never-ending issues that we are facing right now. Some of our dams, due to these sedimentation issues, has reduced its capacity. Some has gone down to even to about 60% life storage capacity. And this is always, for me, is an ongoing process, and it is something that is beyond our control, because the pollution or the sediments that come into the rivers and ending up in our dams is something that has to be managed by other authorities. Okay, so it is always a challenge for us to convince the authorities that something needs to be done, and it is a very costly affair to us. And I think it's not sustainable. We have to look into what is the root cause of the problems, and serious mitigation has to be carried out. Okay, next. On the climate change, this is, I think it is faced by everybody. The climate change has already changed very much the variables, the assumptions that we have carried out in terms of PMP and PMF value, and how it affects, how it impacts the design of the dam. So maybe I would like to share a little bit on what happened in Kenyir. I think some of us may be aware or have seen the documentary last Monday, I think. And what happened on the 27th of February, 2022, there was a huge rainfall lasting for about, I think, maybe 4 days, and we received about 728 millimeter rainfall, which is equivalent to 300 years annual recurrence interval. And the rainfalls has caused a huge landslide near the dam, as well as very adjacent to the dam's abutment, as well as it has caused damage to our spillway. And what happened during that time was very critical, because the landslide has shut off the road to the dams. And we cannot go inside through the road. Only we can only access through either through the lakes or from the river downstream. And we have our, I mean, the spillway due to the fallen rocks and boulders has some damage, and the transmission lines also has been, I would say, wiped out. The switch gear, the switch yard has been wiped out totally, and due to that, we cannot run the turbine. We cannot go in for 1 month. We cannot bring any vehicle into the plant, and we can only bring assistance through the rivers or through the barge from the reservoir. And for 1 month, we have to do something because we have to make sure that the spillway is ready, because the plant cannot be operated. We cannot discharge the water, so the water keep on rising, and we will reach the spilling level if we if that okay, time to go maybe. Okay, maybe okay. I'm on the very last. So what happened that we have to carry out the spillway repair through a very, I would say, a very primitive way of rectifying the problems. And we managed to get the road access 1 month after the incident, and we managed to repair the spillway 1 day before the spilling. Okay, and 3 months after that, only 4 months after the incident, only the switch yard and the transmission line was made ready. On normal occasion, our grid system say that they need more than 1 year, but they managed to do it in 4 months. And after we ran the machine for 2 weeks, we managed to stop the spilling. So these are I think I would like to thank our team in Kenyir. Probably that was why they won the award last night. So I would like to thank them for putting up a very tremendous effort to make sure that the whole thing has been rectified and safe. And the whole slope, as you can see from the picture, is still, we have managed to repair the critical parts of the dams, but the whole slope, I think it runs maybe around 1 kilometers going downstream. It has to be done, and it will take maybe until the year 2024 for us to complete the whole thing. Okay, next. Okay, I will go very fast. This training education, I think I touched just now. Next. Okay, on the future plan, please, next. Okay, these are things that we are looking into. I think we want to enhance the dam's operation and maintenance through more more digital way, in the new for the new technology that we are embarking on the automation, instrumentation, and so on. So I think we need this new technology to manage the dams, so that we can gather more data, we can carry out better analysis and more informed decision making. Okay, On the dam safety chairs, we are already part of the dam safety chair between GENCO and Uniten, where we can easily share the information, knowledge, and so on. Okay, next. On the way forward, next. Okay, these are some of the way forward that we are looking at. No? We talk about integration of the whole system end-to-end, from the design to the end of operation, and also to involve as many people as possible to help us. The instrumentation and monitoring has to be efficient, carry out risk assessment for all dams, enhance the competencies of our people to the very high level, maybe to even the expert level, and the need to do the climate change study to make sure that we are prepared in case of there is some extreme weather conditions. Next. Okay, I think maybe I'm on time. So thank you very much. I'm sorry because I have to leave because I have to attend another meeting at 9 o'clock. So thank you very much again.
Thank you, Yang Berhad Datuk Roslan, for sharing the experience in Tenggis in a holistic approach in the implementation of dam safety programs for TMB dams. Thank you, Datuk. Our next speaker is Datuk Haji Sharbini Suhaili. We'll be talking sustainable hydropower dams. Datuk Haji Suhaili is the group CEO of Sarawak Energy, Malaysia's largest renewable energy developer and primary provider of electricity to Sarawak. Under Datuk Sharbini's stewardship, Sarawak Energy is building upon its 100-year history to advance renewable energy and sustainable hydropower powerhouse in Southeast Asia and digital utility by the year 2025. Leveraging on hydropower, Sarawak Energy's notable accomplishments include 99.2% electrification of Sarawak in 2022, with the remainder to be delivered by 2025, and 73% reduction of the main grid carbon emission intensity from 2010 to 2021. Datuk Sharbini serves as an elected board member of International Hydropower Association and a council member of Energy Transition Malaysia Alliance, a coalition consisting of Malaysia energy leaders to drive energy transition in the country. Datuk Sharbini has also recently appointed as Singapore Management University International Advisory Council in Malaysia. A former Royal Dutch Shell scholar who worked with Shell and Petronas in senior leadership positions before joining Sarawak Energy in 2016. Datuk Haji Sharbini holds honors degree in engineering from the University of Leeds and master degree from Henley Management College, United Kingdom. With that note, I would like to invite Datuk to come to the stage to deliver his keynote. Thank you.
Terima kasih Yang Berbahagia Datuk for the kind introduction. And Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to everybody. And thank you for inviting Sarawak Energy to the second international conference on dam safety management and engineering, or ICDSME2023. It is a great pleasure to be here this morning, and this is a great opportunity for us to share our experience with hydropower dam developments and their importance to the energy transition and socio-economic development, and our commitment to sustainably develop our hydropower dam as a member of the International Hydropower Association. Allow me to provide a brief introduction to Sarawak Energy. We are a vertically integrated power utility and energy development group wholly owned by the Sarawak government. Our vision is to achieve sustainable growth and prosperity for Sarawak by meeting Southeast Asia's need for reliable and renewable energy. Our history, as mentioned by Dato' earlier on, has gone back to about 100 years, transforming from a small utility with just over 80 customers into Malaysia's largest renewable energy developer today as a result of our strategic shift towards renewable hydropower in the mid-1980s. The company is supported by a workforce of about 5,500 diverse talents, serving a total of 760,000 account holders as of last year. And as mentioned, we are on track to realize the Sarawak government's goal of achieving full electrification of Sarawak by 2025, reaching 99.2% statewide and 97.9% rural coverage in 2022 from 56% in 2009. This is very much aligned with the United Nations Sustainability Development Goal number 7, affordable and clean energy for all, and we are committed to supplying affordable, reliable, and predominantly renewable energy for Sarawak and beyond. In addition to the United Nations SDG number 7, we also focus on 7 other goals, goals number 5, 6, 8, 11, 13, and 15, and 17 as shown on the chart. And we believe that sustainable or renewable hydropower development plays a very important role in realizing these United Nations SDGs and enabling climate action. As part of our commitment to sustainability, we were the first corporate body in Malaysia to pledge to the business ambition for 1.5 degrees Celsius, committing to climate action through science-based targets enabled by renewable hydropower. Our science-based targets have been submitted and currently undergoing validation by SBTi, and we hope that the targets will be validated by early Q4 this year. We truly believe that moving forward, the only acceptable hydropower is sustainable hydropower in line with our commitment to the principles of the San Jose Declaration in Costa Rica. We are committed to minimizing any negative impact of our operations while maximizing the positive impacts to the communities and the environment. The next chart will show that our transition mix have transitioned from primarily fossil fuels back in the 2010s to predominantly renewable hydropower today through our Bakun, Murum, and Batang Ai hydropower projects, complemented by our indigenous gas and coal thermal plants for energy security. We have consistently increased the share of renewables in our gen mix and installed capacity since 2010, decarbonizing our grid emission intensity by as much as 73% since then. And we have plans to integrate large utility-scale solar into our gen mix, and will commence the installation of our first 60 megawatt solar project or floating solar project at our Batang Ai reservoir this year. And Sarawak Energy as well has a distinct honor of commissioning Southeast Asia's first integrated hydrogen production plant and refilling station. We produce green hydrogen to power Sarawak's fleets of hydrogen vehicles, which is Southeast Asia's first. One of the key benefits of hydropower development has been our ability to address the energy trilemma of affordability, reliability, and sustainability. Our strategic advantage in renewable hydropower and its lower levelized cost of energy enables Sarawak to offer the most competitive average unsubsidized tariff in Malaysia, and among the lowest in the region at ringgit 28 cent or 6.2 US cents. The increase in capacity in renewables in our gen mix has allowed us to provide electricity to more households across Sarawak, as well as diversify our revenue stream by attracting energy-intensive industries and export customers through our globally competitive tariff and structures. As I mentioned earlier, the renewable hydropower is the foundation of the Sarawak corridor of renewable energy, and SCORE actually is an economic development strategy designed to stimulate investment-led growth in traditionally rural areas of Sarawak. The principal objective of SCORE, and you can see the picture of the Samalaju Industrial Park in Bintulu, is to harness Sarawak's sustainable strategic advantage in production of bulk electricity at globally competitive prices to attract energy-intensive customers to Sarawak for job creation, for job and wealth creation, and make Sarawak a preferred investment destination in Southeast Asia. And with this globally competitive tariff and predominantly renewable hydropower, we are able to record a committed demand of close to 2,900 megawatts from bulk power customers through the power purchase agreement and as well as power exports. So today we have 3 large hydropower plants in operation. The Batang Ai hydro dam was built commissioned in 1985. Bakun was built in 2011, 2,400 megawatts, and Murum, 944 megawatts in 2014. We are currently developing our 1285 megawatts Baleh project, which is expected to be completed around 2027 or 28, following the COVID-19 related delays to the schedule. In line with best practices, our hydropower developments are guided by the International Commission on Large Dams, or ICDSME standards and guidelines, as well as the Malaysian Dam Safety Management Guidelines, or MyDams, ensuring that they are built and operated safely and efficiently. Sarawak Energy has also been an official active member of the Malaysia National Committee on Large Dams, or MYCOLD, since its re-establishment in 2019. The development of all of our new hydropower plants is guided by the International Hydropower Association Sustainability Assessment Protocol, which is now formally embedded in our project development process. Safety is our top priority, so at Sarawak Energy, we believe that everybody who works with or for us has the right to go home safely every day to their family, and to ensure this, we ensure that safety is our top priority in our operation and in our development. Our dam safety policies and dam safety program is to ensure that our dams are safe at all times, recognizing that this plays an integral role in sustainability of our hydropower development to protect our people, our operation, and our environment. And we are fully committed to the safe construction and operation of all of our hydropower dams. The 3 key pillars of our dam safety programs are dam surveillance and reservoir management, dam safety reviews, and emergency preparedness. On dam surveillance, efforts comprise of 5 key activities, which forms a cycle. Firstly, visual inspection at the critical location at the dams, the intake, spillway, side slope, and among others. Secondly, instrumentation monitoring to ensure dams' health condition and for data collection. Thirdly, reservoir management, which involves reservoir rim inspection, catchment monitoring together with relevant agencies, and then analysis and interpretation of data to analyze the data trend and identify instrumentation threshold, And lastly, regular reporting to document inspection findings and recommend necessary rectification where necessary. So these activities are carried out periodically in accordance with each hydro station's respective dam safety manual. Our dam safety reviews are conducted at 5-year intervals. We bring in an independent review panel or third-party international consultant to inspect our dams and provide us with an impartial and unbiased analysis of our dams' performance and operations quality, and to review our instrument data and standard operating manuals as part of our dam safety performance monitoring. The outcome of these reviews determine if our dams are operating safely, and the independent review panel or consultant will also make recommendations to improve our dam safety. Sarawak Energy is fully committed to ensuring the emergency preparedness at our hydropower dams, taking steps to ensure that in the unlikely event of a situation such as dam break, our people and relevant stakeholders know exactly what needs to be done. We have a dam safety emergency plan that is reviewed and improved annually, with drill and tabletop exercises being conducted to ensure dam personnel are being fully aligned with the plan. An integral part of our safety preparedness plan is to have an early warning system installed at strategic locations downstream of our dams to alert the downstream communities in case of emergency. We are also in the process of extending the siren towers further for wider coverage. On top of our dam safety program, we regularly communicate with relevant government agencies before conducting drills and with other stakeholders to ensure that they are kept updated and with the latest development of our dam safety practices, and to ensure that they are prepared for dam safety related inquiries from affected communities members. In fact, this week, the Malaysian National Security Council or Majlis Keselamatan Negara (MKN) is running a crisis simulation drill exercise at our Batang Ai hydropower dam involving multiple agencies and our management team. These exercises help in identifying areas for improvement in standard operating procedures and other protocols to ensure the safety and well-being of Sarawak Energy employees, our asset, and the surrounding communities. As a responsible corporate citizen, we are committed to maximizing the positive impact of what we do while minimizing the negative impacts. In our efforts to be good neighbors and to maintain our social license to operate, we work with the host communities surrounding our project through partnerships and social investments to ensure that they benefit from our presence. In developing social investment program with the host communities, we are looking at 4 main areas. Firstly, education and young people. We have set up education funds for the children of Batang Ai, Baleh, the Balaga Penan and Bakun, as well as the Baleh Youth Skill Training Program. Secondly, environmental management and conservation. We implemented several projects, including the CSR solar project for Pulau Talang Satang and the Tagang system in Murum. The system actually conserves the natural riverine ecosystem. Thirdly, culture and heritage. We support the upskilling of the indigenous Murum, Bakun, and Baleh communities through the handicraft development program. And last but not least, community development and entrepreneurship. We set up the Baleh Women Entrepreneurship Program and Agriculture Development Project towards encouraging the community members to participate in and benefit from the social and economic developments. So these are just some of the examples of the initiatives that we have developed towards building and sustaining long-term relationship with our stakeholders and the communities in the areas where we operate. In 2019, we launched the Sustainability and Renewable Energy Forum, or SAREF, to drive discourse and secure a leading position in sustainability and renewable energy in Southeast Asia. And Sarawak's first renewable energy certificate, or REC, was launched at this event, and it will allow greater participation from like-minded companies or like-minded cooperation in a more sustainable energy future. As I mentioned earlier, renewable energy development has enabled us to explore alternative renewables such as floating solar. We are now developing our first 60 megawatt or 50 megawatt floating solar farm in Batang Air Reservoir. The floating solar construction is expected to start this year and is compatible with our earlier investment in hydropower development, facilitating further decarbonization of our power grid. Beyond our commitment to fully electrify Sarawak, we aspire to become a regional powerhouse, and this is made possible through harnessing our hydropower potential to deliver sustainable development, and through which we're looking at the next staircase of growth, positioning ourselves as the battery of the ASEAN region. We have learned many lessons from each subsequent hydropower development, employing better and more sustainable best practices in our newer projects. And we believe that our experience and expertise, as well as our focus on safe and sustainable hydropower development, will stand us in good stead in our upcoming international joint venture project in North Kalimantan, Indonesia. Sarawak's transition to renewable hydropower development has also opened up opportunities for us to develop transmission interconnection with our neighbors in the island of Borneo. And we believe that the various projects within Borneo will form an important part of the broader ASEAN power grid, which was established in 1997. With Sarawak Energy spearheading and advocating for the formation of this regional grid, we believe that we can contribute to the regional energy transition journey through interconnection from Borneo to the other part of Southeast Asia. In Sarawak Energy, we aim to be the region's most sustainable renewable energy provider. So thank you for allowing us to share some of our experiences and practices in this very important forum. If you would like to know more about our sustainability and renewable energy journey and transition, I would like to invite all of you to join us in Kuching in September this year, where we will be hosting the Sustainability and Renewable Energy Forum, SAREF 3.0, from the 6th to 7th of September this year. The forum will provide further opportunities to discuss renewable energy, hydropower, and actionable solutions for a sustainable energy future. I hope to see all of you in Kuching in September. Thank you very much.
Thank you, Dato' Haji Sarbini. Our next speaker is Lieutenant General Engineer Sajjad Ghani, retired from Pakistan. Lieutenant General Sajjad Ghani is a professional engineer and a soldier who has pursued two parallel career streams for over the last 4 decades. He obtained Bachelor of Engineering degree from Military College of Engineering in 1984. He was awarded Master in Civil Engineering from University of Engineering and Technology, Lahore in 1990. He has Commander Corps Engineers and Quartermaster General, Pakistan Army, where numerous mega construction projects were executed under his supervision. Lieutenant Engineer Sajjad Ghani belongs to Corps of Engineers, commissioned in 1978. He has commanded Infantry Brigade and Infantry Division during SWAT operations. He has been Vice Chief of General Staff at GHQ. He has also commanded corps at Karachi. He hails from Islamabad. He is married and has 3 children. Keen sportsman, and he enjoys physical fitness, playing cricket, and he is an avid golfer. With that note, I think I would like to invite Lieutenant to the stage to deliver his speech. Thank you.
Thank you very much. Thank you. Thank you. Thank you for your introduction. نحمده ونصلي على رسوله الكريم أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم Datin Professor Dr. Laria Muhammad Sadiq, Chairperson of this conference and Co-President of Malaysian National Committee on Large Dams. Professor Dr. Hidayah Basri, Dr. Muhammad Azmi Ismail, Datu Haji Sharabini Suhaili, Sarawak Energy, Dr. Faiz Shah, Dr. Ashworth, eminent scholars, ladies and gentlemen, good morning and assalamu alaikum. It's indeed a great pleasure to be here this morning. But first of all, I wish to register my deep appreciation for the organization of this conference. Event has been organized most professionally with great attention to detail. It has been professionally most rewarding. Thank you for your hospitality and thank you for contributing to knowledge and profession. What I will do is, the aim as is set out for this presentation is to share the best practices, technological advancements, emerging dam safety challenges, and their solutions to ensure safe and sustainable operation of dam projects in Pakistan. Next, please. I shall make my discourse presentation in the sequence as shown on the screen. Causes of dam failures in the world, Pakistan dam safety, engineering and management, Pakistan critical dam safety factors, and I will present certain case studies on Tarbela Dam and the Amir Basha Dam. And may I somebody state that these are one of the largest dams anywhere in the world. Tarbela Dam is a largest earth-filled dam in the world, built in 1976. And the Amir Basha Dam is world's tallest roller compacted concrete dam, standing at a height of 272 meters, being built over the great river Indus. So the scope is big, so is the challenges are big, and so are the solutions that are big and technically most testing. Next, please. Why dam safety is important? Consequences of failure of dams are unacceptable. This goes without saying. However, history tells us that dams have failed in the past. And the profession has learned from these dam failures, and we endeavor to ensure that our future dams are safe. Next, please. Much of the thunder from my presentation was stolen by the president of the MYCOLD yesterday in his presentation, but then, nonetheless, these are the causes of dam failures in the world, and largely they the contributing factor is the overtopping, which is 44%. Gates fail to open, and there is inadequate spillway capacity. But a very large contributor is piping. Now, the piping is 34%, and this occurs quite often because of foundation failure, embankment, and abutment failures. The other causes are structural and some miscellaneous, which contribute to 20 or 22%. Next, please. Let's see videos of some of the dams which were not covered yesterday. Could you open the audio as well, please? Next, please. Just highlighting salience of a case study, which was a Taton Dam failure, and that was in 1975, and it was a type of earth-filled dam standing at a height of 305 feet. Dams are vulnerable, very vulnerable at their first filling. So in the first filling in 1976, catastrophic failure occurred due to development of sinkholes and piping mechanism. So these are one of the most important causes of failures of dam, that is the sinkhole and piping mechanism. The embankment breached within hours after the first sign of seepage, and usually the response time to mitigation is not available, and resulting release of water inundating an area of over 300 square miles, which traveled a distance of 150 miles downstream. The dam failed due to design and construction flaws. Next, please. Next, please. I'll give a very brief snapshot of what WAPDA is. It's a Water and Power Development Authority of Pakistan, and our charter is integrated development of a water and hydropower project for socio-economic uplift of Pakistan. And we have developed storage dams of more than 20 million acre-feet capacity. As I said earlier, these are one of the largest. And we are also largest suppliers of hydropower, contribute over 95% of country's hydropower. We have the institutional capacity to plan, develop, operate, monitor water and hydropower projects. We are financially viable for supporting future expansion plans. And WAPDA's operations are aligned with Sustainable Development Goal, UN SDGs 6, 7, 8, 9, and 13. Next, please. At this point in time, we are operating 22 operational projects, and we are generating close to 9,500 megawatts. And as I said earlier, the storage capacity is 20 million acre-feet. Our under construction projects are as big indeed, as mega indeed. And at present, we are undertaking construction of 4 mega projects, anywhere largest undertaking in the world at any point in time. And generation capacity that we are now adding is about 11,400, storage capacity of 10 million acre-feet. And the cost of these projects, tentative cost of these projects, which are due to be completed in the next 4 to 5 years, stands at US $22.5 billion. And as we are planning to complete these projects, the other on the drawing board, which are ready for construction, are hydropower projects of about 17,800 megawatts, and with an additional storage capacity of 8 million acre-feet. Next, please. So when we have such large undertakings, then as I said, the challenges and response dilemmas are also as mega, significant, and big. So what do? The first thing we do is to create awareness amongst public, dam owners, and government officials. We empower them by technical training and empower on-site personnel. Obviously, everything has to come under a legislation, so that cover needs to be provided. And this is what gives birth to the establishing dam safety programs. One cannot achieve anything significant unless appropriate financial grants are made available, and thus necessary funding is provided for carrying out dam safety measures. Next, please. So we develop and exercise early action plans. We integrate early detection of failures into emergency planning. We put in place effective security mechanism, and obviously the modern world is empowered by AI and technology, so we keep our instruments updated, and data is IT-enabled collection, interpretation, and decision-making. Next, please. How do we articulate the dam safety engineering and management? It is done at 3 tiers. At tier 1 is the project office, which carries out routine inspections, emergency preparedness planning, and rehabilitation options. At tier 2, we have a dam safety organization at the federal level. This provides surveillance through inspection and instrumentation and deficiency investigation. At tier 3, we have periodic inspection, third-party independent experts coming from around the world who carry out comprehensive periodic review of dams through national and international protocols by a renewed expert. This is done almost every 5 years. Next, please. So how we organize these tiers? At the tier 1, which is the project officer, the regular inspections are carried out, and they are empowered by 4 departments at every project site: an instrumentation division, a seepage and geology division, movement control survey division, and a sedimentation survey division. This is the basic tier at the project level. Next, please. At the tier 2, we have annual inspection, which are carried out by dam safety organizations. They are into a central directorate of inspection and coordination, and then we have 3 different regional directorates which carry out the dam safety: a northern zone, central, and a southern zone directorate, which are empowered both in terms of manpower, equipment, and skills. Next, please. Now, what are the critical dam safety factors? Pakistan, as indeed the entire world, is at the mercy of the climate change, and we are prone to both phenomena, flood and seismic activity. So, and obviously, flood, seismic activity is also has become significantly important during the recent years. Obviously, as elsewhere in the world, sedimentation continues to be a challenge. Next, please. How we do that? A technological awareness through instrumentation is absolutely necessary. So we have put in place hydromet stations across the rivers and stream. At this point in time, more than over 200 hydromet stations have been deployed. And if you would see, their deployment is essentially in the north. That is from where we draw our rivers and our waters. Next, please. Equally important are weather stations. There are 38 weather stations that monitor rain and other weather-related events. Next, please. This is how the surface water has been available in Pakistan through years. And you would see that from an average of 144 million acre-feet, the drought years have 109 million acre-feet, while the average years have about 130 million acre-feet of water available. Next, please. Sedimentation is a big challenge, and as this screen would show, that we receive about 200 metric tons of sediments in River Indus annually. Next, please. Seismic activity. This is most significant. Pakistan lies in an active seismic zone, and all dams in Pakistan are designed based on site and seismic hazard studies following international practices. These studies are carried out and vetted by top experts in the world, and WAPDA maintains 29 micro-seismic stations at every dam site. WAPDA maintains a rigorous network of strong motion accelerometers to monitor the structural health of the dams. Next, please. These are some of the stations which indicate critical dam safety factors and seismic activity. If you look at the key, the areas that are shown in brown and dark brown and orange color are the ones that are most vulnerable to seismic activity. Next, please. Critical seismic factor, as if you would see on this slide, the safety evaluation of earthquake is given, and the peak ground acceleration is also indicated. And the figure, a look at the figure will tell you how intense these could be in areas in which our large dams are located. In Terbela, it's 0.65 G, and Deamir Basha Dam, which is under construction, it's designed to cater for 0.64 G. So these are huge values. Next, please. So then, what is the dam safety phases that we need to consider? Safe design to start with, and continue to review it. The challenge is how to cater for all these design parameters or these risk factors for structures that were built 50 years ago. Construct to the international standard and adopt changes in design due to site conditions observed during construction. This is significant. And continue to operate safe and sustainable. Resort to periodic maintenance. Next, please. Very quickly, 2 case studies in safe operations and maintenance. The largest earthfill and rockfill dam in the world, Tarbela, height 470 feet, earth and rockfill. And look at the life storage capacity when it was built, around 10 million acre-feet, good enough to submerge at least 30% of the country. Installed capacity is about 5,000 megawatts. Next, please. Soon, when this dam was built, 362 sinkholes were developed in upstream blanket due to open work gravel in river alluvium. And these sinkholes by no means were small. As the dam was big, this large sinkhole had a diameter of about 40 feet, and deepest sinkhole had a diameter of 13 feet. And it occurred because of excessive erosion. Now, WAPDA at that point in time adopted innovative measures, that is sonar detection and filling through large barge dumping with expert advice from one of the renowned world professor at that point in time, Dr. Arthur Casagrande. And with formation of sinkholes in many clay core, the professional learns about self-filtering criterion from this incident. WAPDA executed first use of large-scale roller compacted concrete in the world to address excessive erosion of the stilling basin of the spillway. As you would see, next please. As you would see in this slide, you could see the size of the sinkholes. And towards the right of the screen, you would see a large barge carrying the filter material. So these large barges were used to dump the filter material in the sinkholes. Next, please. And this is a slide which shows when this dam was built. It had a original bed elevation of 1,300 feet above the main sea level, and it is now, due to sedimentation, lost about 100 feet. The average bed level is now at 1,400 feet above the mean sea level. And this is the act of the sedimentation. Next, please. So high sedimentation, that's the issue, and the challenge is that it reduces irrigation supply, damage to power installations, flushing causes damage to downstream infrastructure, and blockage of low-level tunnels due to liquefaction of sediment data. What are then solutions? The sedimentation is the largest challenge that dam operators face through the world. Short term is reduce the minimum operating level from 13 to 1,402. Now retard advancement rate of the sediment from 0.3 miles per year to 0.16 mile per year. And in the medium term, intake of tunnel 3 and 4 have been raised. And in the long term, there is another dam that is being built upstream of Tarbela, which will enhance the life of the reservoir by 35 years. Next, please. This is a brief case study of the under construction tallest dam of the world, standing at a maximum height of 272 meters, but lying in an intense seismic zone, also prone to GLOF, which is glacier lake outburst phenomena. So the data is shown with a light storage capacity of 8 million acre feet and a generation of close to 4,500. And as we were undertaking the design, the seismic activity, unprecedented floods mandated a review. Next slide, please. And this is a comparison of the dam. If you see Deamir Basha Dam, height 272, and look at the RCC volume, It is 17 million cubic meters. And look at the number 2, number 3, and number 4 dams. Number 3 is also being done in Pakistan. And you would see the volumes are by nowhere comparable. These are very large undertakings. Next, please. Then this one dictated feasibility in 2000 and 2008, and because of seismic activity, we had to change the G from 0.46 to 0.64, and safety check, flood, we changed the reservoir operation criteria, and sedimentation study changed the sediment management concept. Next, please. This, on the left side, you see the tender design, and on the right side, you see the revised design due to addition of seismic and flood activities. An additional toe and about 17.5 million cubic meters of concrete was added. Next, please. And a major design change from spillway, we came back to free overflow spillways. And from 7 dam outlets, the dam was revised to 11 outlets. Next, please. Changes in powerhouse cavern, waterways, shifting of left power tunnels, all of these had to be undertaken. Next, please. In the gray, you would see the tender power scheme. In the orange, you would see tender power scheme, and in the grays, you would find the revised power scheme and the review that has been undertaken because of the seismic and other activities. Next, please. So, state-of-the-art knowledge, various organizations provides guidelines, and including ICOLD, and we also draw sources and inspiration from other sources of knowledge. Next, please. Wabda dams have withstood safety against all damaging events, earthquakes, floods, etc., which is a testament to Wabda's commitment towards dam safety in all phases: design, construction, operation, and monitoring. Next, please. And this is a slide that you will all love. Thank you very much.
Thank you, Lieutenant General Engineer Sajat, for a very good presentation. I think with that, I'll pass back the microphone to our MC, Dr. Zhu. Thank you.
Thank you very much, Dato' Azmi, and all eminent keynote speakers. So, ladies and gentlemen, next we shall proceed with plenary and parallel sessions. So, we shall break out into 4 rooms: Sarawak, Kedah, Selangor, and Perak. I would like to remind all participants that the Dam Safety Forum will take place this afternoon at 2:45 p.m. here in Sarawak room. Also, I would like to take this opportunity to invite all participants who have not registered as MYCOLD member to consider becoming an official member of MYCOLD. Please visit the MYCOLD booth at lower lobby for assistance. So, ladies and gentlemen, have a fruitful plenary session. Till we meet again. Thank you.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. And first of all, I would like to extend my big thanks to MYCOLD for inviting me again after the first ICDMSE in Penang, and especially to Professor Datin Laria. And I'm sorry that I'm a little bit in a rush because my turn seems to be 40 minutes late than the schedule. And I would like to share what Professor Laria is asking me, telling about the innovation in dam development in Indonesia. And basically, it consists of three parts. The innovation consists of early risks to effectively respond to the climate change. The second is about the dry dams for flood reduction in Jakarta metropolitan city. And the last one is reservoir utilization for solar hydro development. Next, please. About the early risks, probably this could be one of the new examples that we can see on how we respond quickly to the climate change. Previously, what we have done to put the release for the facility required during flood season is using the facility for environmental flows or using the intake, bottom outlet, or the spillway. But recent experience shows that extreme floods need more facilities to release the water earlier than the expected schedule. For that reason, new dams in Indonesia currently add a special structure for early release next to the spillway. Next slide, please. And this type of early release is designed based on hydrological data in addition to the capacity of the existing spillway. But we have to remember also that there is another important information regarding the capacity of the river at the downstream area. Because we cannot forget that people at the downstream area shouldn't be having additional burden if we release the water more than the capacity of the river. So the operation of the gates for the early release starts when the Water Bureau predicts incoming major floods. So a few days, a few weeks before the incident, we will have to be ready to operate the new facility of early release. Next. The example of this early release have been built completely in Sadawarna Dam in West Java, late 2022. And before that, there were several flood events in the downstream area of the city of Subang. So during the rainy season, the reservoir levels need to be gradually lowered before the peak floods. And how to do that? This early release has been installed 1 to 2 meters below the crest of the spillway with gates. So when we know that there will be a big flood coming, so prior to that level of the crest of the spillway, we open already the gates so that gradually the water of the reservoir will be lowered. And later, people will know that the river flow downstream is already getting more water from this opening of the early release gate. Next, please. The second introduction of new things for flood reduction in Jakarta metropolitan city. We have built completely 2 large dams at the upstream part of Ciliwung River in West Java. And this river enters the south part of Jakarta with floods in most of the year. So during the rainy season, the discharge is retained in this reservoir, except in a certain quantity of water, the water will continue flowing through the conduits. The conduits was previously used for diversion conduits during the construction, but there is no gates at all, meaning at any point of time, the water can always flow through these diversion conduits that become the bottom outlet at later stage. Next, please. I will show one by one of these two dry dams. The first is the Ciawi Rockfill Dam with 55-meter height and 335-meter length. The capacity in full will be around 6 million cubic meter. And you can see on the left side in the cross-section the two conduits, and on the middle part you can see the completed inlet of the conduit with a kind of concrete trash rack to avoid all this garbage and all this kind of trash to enter this kind of diversion channel that becomes the bottom outlet. And on the right, you can see that Ciawi Dam is located quite high in the mountain, and that is the challenge that we have, that heavy rainfall happens in most of the days during the year. So the construction of the clay core and also for the random material must be stopped if rain is coming to that area. Next slide, please. The second dam is Sukamahi Dam, which is another rockfill dam with 50-meter height and 170-meter length. The reservoir is 1.6 million cubic meter. So you can see on the left side the location with the star, and also the right side you can see the complete structure of this dry dam, which will be always empty if there is no flood. But during the flood, most of the water can still flow through the diversion conduits that become the bottom outlet. But if the water is so high, then it can be retained in the reservoir unless it reaches the spillway level. So for this reason, this dry dam could also be considered as a dam for water conservation in the area. Next slide, please. The third innovation that we have developed is the utilization of dam reservoir for solar hydro development. So the first floating PV is already undergoing now in Cirata Dam with commercial operating date scheduled for Q4 of this year. Currently, it occupies less than 5% of the maximum area because we would like to see the negative impact if the area covered by floating PV could hamper the reservoir as well as the dam structure. So when completed end of this year, the floating PV of 145 megawatt peak will complement that 1,000 megawatt hydropower already in operation in Cirata since 1988. Please note that currently we completed already the guidelines of FPV in dam reservoir related to the dam safety after having stakeholders meeting until November 2022. And currently we are also in INACOLD actively participate in the preparation of the ICOLD Technical Committee T at all stages of the drafting of ICOLD bulletin concerning floating PV in dam reservoir. Next slide, please. For this one, I can go into further details that the Cirata is actually a difficult example as a pilot project. Why? Because the height of the dam is 125 meters and the water level going to the bottom can reach about 100 meters. And long discussion how to secure the dam safety we have to convince the developer for almost 2 years to take into account what should be done to secure the dam, the spillway, and the intake in the case of any failure to the floating PV, either through the anchoring, the mooring system, and that is the reason why the anchoring and the mooring system on the bottom right, you see it is very, very carefully designed. Next, please. Now, we learned from the failure of floating PV in Yakamura Dam in Japan. And the critical issue, the same thing also there, where the anchoring was losing their power because of the typhoon. And for that reason also, in our case, we add the special protection to the intake, the spillway, and also for the dam. And we are now monitoring the construction of this anchoring and mooring system starting March and should be completed around September or October this year. Next slide, please. The last innovation that we have done recently is introducing the asphalt core concrete, concrete embankment dam. And it is firstly built in Indonesia, and the location is in Bali. Why we have this kind of solution? The problem is actually because of no availability of clay core according to the previous design. For what reason? Because the owner of the land for this kind of bore area refused to give the land for the clay material, and we do not have another choice rather than trying to innovate something, and we use the asphalt core and having a kind of support from the Norwegian Geotechnical Institute laboratory in Norway, and we sent the samples there until we got the final mix design and the method of construction for this first asphalt core embankment dam. Next slide, please. So what we have done is trying to modify the paver and also all kind of equipments which is available in Indonesia without waiting for special equipment coming from Europe. And we have also to use natural sand instead of crushed sand. And we conduct also traxial tests on site in later stage after learning from the experience. Sending materials to Norway takes time and so forth and so forth. So the detailed design and construction by Indonesian experts for this asphalt core has been successfully conducted, as you see on the right part of this slide, showing it was completed a few months ago, and we are really now happy to see 2 more asphalt core dam in progress to be built in Bali Islands also, and another in Timor Islands. Next slide, please. So this is the closing remarks. Dam safety is the paramount at all stages of the hydropower and floating PV development. And innovation in design, construction, and operation of dams shall be encouraged by the authorities to achieve a more sustainable development. And last slide will be next slide please, will be my appreciation to MYCOLD, and as well as to invite you to see us at the World Water Forum, May 2024 in Bali. Thank you very much, and have a successful conference until end of this week. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Yes.
Thank you very much, Dr. Aris Farman, for managing the time so well and also for delivering some very important points for us. I'd like to thank Dr. Farman for his time and wish him the best of journeys back to Indonesia. Thank you for making time. Well, that's technically the end of the session, folks. And thank you for coming in. I am glad that you were able to make at least some part of this excellent presentation. And I think the innovation that was discussed here is something that you might want to follow up on. With that, I'd like to thank you all. And we close this particular session. There's more coming, but I'll flip off now and then come back shortly back to you. Thank you. Please don't go away. Good to see that we have more people now coming in. Welcome to the oral presentation session. We have a number of papers already planned, but as I'm not aware if the presenters are already in the room, I will announce the names, and if you are here, we'd invite you to come here and we'd like to listen to your oral presentation. If we don't have somebody here at the moment, we'll announce the next one and so on, and keep going and cover as many people as we can. Right, so the first theme for the oral presentation today is dam rehabilitation. And the title for this presentation is Rehabilitation and Remedial Activities in the Historical Abbasabad Beshahar. And the authors are Zarsazi, Hassan Ali, and Zarsazi. If any of the authors are here, we'd welcome them to join us on the stage. Okay, no worries. The second presentation is Dam Safety Review and Risk Assessment. The title of the presentation is Dam Safety, Highlighted Issues and Reliable Assessment for the Sustainable Dam Infrastructure. Authors are Nurazwa Muhammad Bashar, Muhammad Remi Rezaini, Muhammad Arif Zainul, Muhammad Sharizal Abdul Aziz, Ahmad Zafran, Ahmad Maslan, and Muhammad Hafiz Zawawi. If Hafiz is here or other friends are here, please join me on the stage. If not, I'll move on to the next one. We are here. And you are, yes, would you like to join? Please come over. And we can do it very quickly. Please join me on the stage. And you are Nurazwa? Yes, please come, Nurazwa. And allow me to let you introduce yourself quickly. And we'd like to try to keep to time because we're running behind.
I'm trying.
Yeah, thank you very much.
Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good morning to ladies and gentlemen. Actually, my name is Nurazwa binti Bashar, working in UITM and currently doing PhD with USM. So today I would like to present with all of you about dam safety, which is the highlighted issues and reliable assessment for the sustainable dam infrastructure. Okay, so thanks. Okay, in my presentation, I will cover the overview of the review, the introductions, the dam safety, the sustainability, and the SDGs, which is under United Nations. Review objective, the review process, which is some sorts of scope of works, the review questions, as well as the review tables and the figures to support the issues, the conclusions, and ended up with the future research directions. Next, please. Okay, this is actually the overview of the dam safety, which is support the sustainable dam infrastructure. As you look at here, it have several divisions of the goals, issues and challenges, pressure, mechanism, dam safety monitoring, and the future direction, which is under the SDGs, it will cover the number 6, United Nations SDG number 6, which is clean water and sanitation, and number 13, which is the climate actions. Okay, we'll proceed with the next slide. Next, please. Okay, in my introductions, this is some of the questions that I will cover, which is the potential threats to the dam infrastructure sustainability, the potential mitigation measures to support the dam sustainability, the dam safety concept, the dam safety assessments to support the dam sustainability, and the triangulations between the dam safety with the dam sustainability and SDGs. Okay, and finally, with the integrations of holistic approach that may support the dam sustainability. So actually, over a few years, the operational breakdowns and dam failure, primarily aging and the threatened types, were identified as main of the potential threats to the dam sustainability over a short and long terms period. So added with the high dam and old dam, which is registered with the ICO. Okay, the presence of this, the presence of the climate change factors across the globe was added and worsens the sustainability, which is the conditions of the infrastructure itself. Okay, which is caused the alterations to global meteorological patterns such as hot and dry climates, as well as the presence of the intense rainfall events. Okay. Okay. How about the potential mitigation measures? So therefore, warning system should be conducted to minimize the risk, okay, which is related to the dam safety. Okay, on the first hand, the safety assessments is vital, and it will provide an early protections of the event or detections of the events or incidents, okay, before the actual events, okay, which is related to the detections of the changes, okay, which is impacted from the events. Okay, some of it, okay, the rehabilitations or the maintenance work can be expedited, okay, either in terms of the non-structure measures or structure measures. For example, the developments of the emergency reference plans, the guidelines, the design standards or codes of ethics, okay. And then the structure measures will cover the design part, which is the designs of the reliable spillway, okay, to convey for the appropriate or at the PMF or PMP, okay. And then the dam safety concept itself will cover the safety parts, okay, the structure safety itself, the monitoring system, the operational safety, the maintenance work, and the emergency planning response. Okay, so as you look at here, you can see back to RQ1. Back to RQ1 slide. Okay, as you can see here, okay, the some of the highlighted issues with the safety of the dam. Okay, the first slide before this slide, the previous slide. Okay, this one. Okay, so as you look at here, some of the highlighted issues is the static and dynamic loadings, okay, which is contributed to the worseness of the dam infrastructure, especially the spillway, okay, and the steering basin sections, right, with the presence of the turbulence flow, okay, that give impacts to the downstream section that can cause erosions and sedimentations, okay. So next one is the hydraulic characteristics, the climate change instability, the structure conditions, and then behavior changes in terms of the periodical practices. Okay, the next one, next slide please. Okay, the vibration. The vibration is the some of the huge factors. Okay, that may give impact to the dam infrastructure, especially to the gate. Okay, gate vibrations, the net vibration, the spillway vibrations, and mainly, most of it coming as well from the turbine, okay, and pump. Okay, next one is the technical design limitation, which is design flaws, okay. Next, the monitoring data, presence of the missing data, the obsolete data, okay, errors or anomalies. Next one. Okay, instrumentation and monitoring, which is limited coverage area, okay, that can capture the actual dam conditions. geological or rock mechanics and geotechnical section, which is in terms of slope failure, sand liquefaction, settlements, okay. Downstream degradation in terms of erosion and sedimentation, and most of these issues were already mentioned by our plenary speakers before and keynote speakers. Okay, next. This is the summary for the impact factors and the outputs, which is the impacts relationship, okay, factors and impact relationship between the climate change impact with the environmental factors, and then the dam behavior responses and environmental impact. As you can see here, most of it, the presence of the climate change may alter the conditions, okay, the environmental condition with, for example, with the presence of the earthquake, the natural hazards, okay, the frequent appearance of the natural hazards such as earthquake, flooding, right, from the intense rainfall events, okay. And then the presence of the hydrostatic pressure, the seasonal variations, the seepage intrusion, and the dam behavior responses may appear in the forms of dam displacement, again, the concrete, the concrete stress and strains, concrete cracking, and internal erosion. And the worst one is the downstream part, which is impact, that give impact, that receive impact from the high velocity flow, which is downstream erosion and sedimentations. Next. So here is the highlighted points on the dam safety assessment, which is focused on the monitoring. So as you look at here, this is some of the summary, okay, taken from the previous researcher in the Elsevier and WAS journal, okay. So as you look at here, the Atatürk Dam, Turkey, the Hydroelectric Dam in China, okay, in the United States and Canada, okay. So as you can see here, there are several types of monitoring system were used. For example, the real-time one, EnviroSat or Sentinels, and satellite one, okay. And then the usage of the applications of the numerical modeling, okay, the data-driven predictor model to predict the future events, okay, to preserve the infrastructure, okay, and as well as on-site inspection and surveillance, okay. Next one. Okay, this is the summary. As you look at here, you can see some of the instrumentations, okay, and monitoring system, GPS, radar as mentioned earlier, okay, and on the left one, you can see that, okay, the seismic and structure head monitoring system for Dam, Portugal, okay, which they have the vibrating system to detect for the seismic activity, okay, for example, the accelerometers, okay, to detect how many is the hertz or how high is the hertz, okay. Next one. So this is as well the summary, okay, for the instrumentation and monitoring system. You can see the impacts of the climate change, okay, towards the dam infrastructure. So as you can hear, there is a lot of sensors and instrumentation that installed in the real dam, which is a satellite one for the water level detections, the sensor, which is abnormal foundation detections, satellite or sensor for the seepage intrusion detection and concrete cracking, okay, and as well the bedrock detection, okay. So from that instrument, okay, it will be data processing stage, okay, where the data will be processed, okay, in the forms of analog data to digital data and saved at the base station, and then as an input to the predictive models, either numerical, statistical, data-driven, or hybrid types, okay. So in the forms of static and dynamics, which is, for example, experimental model analysis or operational deflective shape, right? And from that, the dam behavior change relationship study and damage action can be conducted, okay? And then the prediction models as well can be cross-validated with the physical data, okay, which is from the visual infections, the real dam sites, okay? And then will be the performance of the numerical model will be validated in the forms of R squared, which is regression, RMSE, and MAE, okay? To get the error, okay? And as well, this one will expedite the decision-making process in terms of technical and non-technical measures. Next. Okay, as a conclusions, okay, for the dam safety issues, the identified factors should be really considered, okay, if we would like to highlight the dam sustainability, because dam sustainability require a very long journey, okay, which considerations that we need to put up in the forms of integration, which is holistic integration in between the policymakers, the multidisciplinary experts, okay, and dam safety assessments, okay, which is the things that we should bear on, which is in terms of physicals or on-site or physical models or predictive models in the forms of numerical simulations, statistical, data-driven, or hybrid approach. So that's all from me. Thank you.
Well, thank you very much. That was very nice, and it's good that we're trying to keep or pull back time that we've lost since the morning. We're going to make a changeover now. So a number of oral presenters have not joined us or not informed us of their presence. So Professor Laria has advised that we move on to our next session, which is a kind of a much more expert level session. So I'll just go straight to our next distinguished speaker for the morning. Dr. Martin Wayland is here with us today. He's chairman of the Committee on Seismic Aspects of Dam Design at ICDSME2023. Dr. Wayland has been chairman since 1999. He has a long and distinguished career in dams and particularly seismic design, and has been chairman of the Earthquake Committee of the Swiss Dam Society, as well as a series of extensive consultations across more than 35 countries, with in particular to dam seismic design of dams. Dr. Wayland obtained his master's and his doctoral degrees in civil engineering from the Swiss Federal Institute of Technology, ETH, in Zurich, in 1971 and 1978 respectively, and he was an associated faculty member of ETH from 1978 to 1980. In fact, he offered the first course on earthquake-resistant design and structures at that time during his stay at ETH. From 1980 to 1990, the Asian Institute of Technology, where I also come from, had the pleasure of having Dr. Wayland on our faculty, and he taught earthquake engineering and structural dynamics, among other structural engineering subjects. He was a member of the Structural Advisory Board for the Panama Canal Authority for the recently completed New Panama Canal. He was also a member of the panel of experts in a whole series of countries on advising on large dams, including Colombia, Ethiopia, Iran, Latvia, Pakistan, Papua New Guinea, Sudan, and others. He is the advisor for the newly established Dam Safety Directorate of the government of Ethiopia. During the last 40 years, he's worked with over 115 large dam projects and has visited many more. Dr. Wayland is an honorary member of ICDSME2023, received his honorary professorship from Hohai University in Nanjing, China. He is a visiting professor at the Three Gorges University in China and a distinguished adjunct professor at the Asian Institute of Technology. Dr. Wayland is an honorary member of the Swiss Society of Earthquake Engineering and Structural Dynamics and a member of the Civil Engineering Division of the Swiss Society of Engineers and Architects. He's authored over 300 technical papers in the field of dam and earthquake engineering. Ladies and gentlemen, it is my pleasure to invite Dr. Martin Wayland onto the stage, and we're going to have a very engaging and extensive presentation and make up for some of the gaps we've had since morning. Dr. Wayland, please.
Okay, Dr. Shah, thank you very much for this lengthy introduction. Okay, I'm sorry. So I think we have some time for my presentation. And the topic was already announced, is how to deal with the many hazards affecting dam safety. Up to now, some people have talked about different hazards, but basically I try here to have a broader look than what people have looked at really up to the conferences which were held here. So if we look into the hazards, I listed them here in red. Number one, we will talk about natural hazards. Number two, we will talk about man-made hazards. They're much more difficult than the natural hazards. Nobody has yet talked about that. And I will talk about site-specific and project-specific hazards. Okay, so that is my outline. So if we look, we start right away with natural hazards. And if you have natural hazards, typical ones are floods, I would say, are most relevant here in Malaysia. But we also have earthquakes. We have heard from Pakistan, where floods and earthquakes are the dominant ones. But we also have landslides, and we have extreme weather conditions. And as somebody has mentioned already, we have climate change effects. I would like to say these hazards which I'm listing here are basically time-dependent. Not only climate change is time-dependent, basically also all the other hazards are time-dependent. And as dam engineers, we must know how to deal with time-dependent hazards. Okay. Now, if you have different hazards, there are different protective measures which can be taken, and they are listed here. Number one, if you have enough time, you can do rehabilitation. If it is more urgent, like flood or some threats, you do a partial drawdown of a reservoir because you can increase the safety of your project. Number three here is if the hazard is larger, you have to try to make a full reservoir drawdown. And in some cases, you have to do, if it's going very fast, you have to do evacuation. And in a case of earthquake, you cannot take action. There are warning systems. We have been involved in warning systems, for example, in Istanbul and in nuclear power plants in the Baltic states. The warning time is only 6 to 8 seconds. So if you have warning times of that short, it's not like climate change where you have tens of years. We have been dealing with warning times of 6 to 8 seconds. You must be extremely fast. Okay, so we have this kind of experience. Therefore, we feel, looking from the earthquake point of view, the climate change hazard is quite comfortable in terms of time compared to those I am mentioning. So the most difficult hazards are those where basically only post-event evacuation is possible, as in the case of earthquake. Therefore, the earthquake hazard is basically one of the most difficult hazards. Now, let me just look. Sorry, I'm just going in the wrong directions. Now, if you look into a flood hazard, usually people think the water is clean. This is a picture taken here from Myanmar in 2015. You see this is a dam newly built, and during a heavy rainstorm, you see here the huge number or the huge amount of floating debris. And this floating debris, it blocked here, you see, this is a free flow spillway. Usually if you have spillways for dams, the safest ones are free flow, because then you do not have a headache about operating gated spillways. These are basically a headache. But you see, if you have this huge amount of floating debris, it even blocked here this free flow spillway, which are considered the safest. Why does it move like that? Okay. Can you put the full screen? Yes. Okay, so this is the dam where the spillway was blocked by this floating debris, and you see here the water level was increasing. This was a newly built dam, and basically the water level almost reached the dam crest, and it would not have, was almost close to, let me say, failure. It was a difficult situation. So if a spillway does not work, you may end up in overtopping, and for embankment dams, overtopping leads basically to failure of a dam. Okay, this is a picture from Pakistan. Okay, the general has left already. I just wanted to say what we have to look at in mountainous regions. We have a lot of sediment transport. You see here it is quite large blocks. This is a diversion structure. This diversion structure is almost covered by large blocks. You can hardly identify it here. This is a concrete weir, and this is a diversion structure. Even the gates were damaged or destroyed partly by these large boulders, and here was the intake then for a hydropower project. Okay, we have overtopping, for example, of concrete dams during construction. As we see here, this is Nam Ton 1 in Laos, which was recently completed, an RCC dam, and on the other hand, on the right, you see here the overtopping during construction of a Tekesi arch dam in Ethiopia. So overtopping of concrete dams basically is not a major problem. It causes not failure of a dam as in the case of embankment dams. Next, please. Yes. Okay. I would like to show a few examples of dam failure which are not so known, but there were a few significant failures in Italy. This is the Zerbino Dam in Italy. Is a masonry dam here, and it was overtopped, and because it was overtopped, the sliding stability of dams which are actually of moderate height, if you have overtopping, the sliding stability actually decreases quite significantly. If you have overtopping of a 100-meter high dam by 2 meters, it doesn't change your sliding stability substantial. But if you have a 10 meters high dam overtopped by 2 meters, basically your dam may be washed away. And you can see here when we visit, or when I visited this dam here, this is the abutment here. The dam was washed away. If you see it there is actually nothing left. Okay, this is just a picture from Germany from 2021. This dam was, as you can see here, it was overtopped. There is this road, and this road basically protected even the dam, and you can see here, even the bushes here, they protected the creation of deep holes. This dam was, I would say, was overtopped by about 40 centimeters. The problem here in Germany was that they have not updated, in my opinion, the safety flood. So the flood which has occurred there was basically twice or even higher, more than twice the design flood which they have taken into account. So this should not occur. So some people claim that to climate change. It is not climate, it contributes, but the reason is not climate change, but it is people have not adopted the let me say, flood safety criteria, which is the main reason, but nobody will admit that, and they will say this is a typical case of climate change. It was already unsafe before. Okay, so there are quite a few cases where people like to argue that a failure or some damage is related to climate change, but actually it was already a design or a safety deficiency of that project. Okay, does it come? Somehow this doesn't come. Okay, this here is from the US in 2020, and you may have also read about tailings dams which have failed in Brazil and also in Australia and Queensland in recent years, and people have argued it was static liquefaction. Okay, and some people were arguing there was a magnitude 2.5 earthquake which may have triggered that. I would say people have not done a proper safety evaluation, because static liquefaction, you know, should not take place. If you would do a proper safety evaluation, you have to take into account some seismic aspects. This is already very old. So if you would do include in your safety evaluation the seismic loads which we have omitted, you would have found easily that this dam was unsafe. And when finally they say static liquefaction, anybody who is doing with earthquakes knows if static liquefaction has occurred, this dam has never been safe for earthquakes. Okay, this is a typical case. So people like to talk about static liquefaction. It is a kind of people not doing the job properly. Somehow it goes next. Okay, here is from the Himalayas. We see in Uttarakhand in 2021. We had here from high elevation, we had a mixed ice and rockfall which propagated at high speed along this valley, and it, as you can see here, it washed away 2 power plants. Okay, what can we say here? Basically, in such environment, you cannot build run-of-river power plants. It's a mistake. Here, basically, it would only be possible to build a reservoir. If somebody is building something, you would have to build a large dam with a huge reservoir which can absorb, let me say, the mass, the volume of a sliding mass. Otherwise, if you are not able to do that, it will just destroy these run-of power plants, as this has been the case. So run-of-river power plants should not be built at such location as has been done. Next one. Okay, we see here there are from earthquakes, we have also some natural dams, and the world's highest dam is in Tajikistan, is a left one. The volume is 2,500 million cubic meter, and it is about 650 meters high. The highest man-made dam is about 300 meters. So the highest, let me say, natural dam is twice as high as the largest man-made dam. Most people don't know it. This dam was triggered by an earthquake more than 100 years ago, and it is still there. There is still some progressive erosion processes going on which may threaten the river Amu Darya, which eventually goes into the Aral Lake. On the right-hand side, you see the landslide dam created during the Wenchuan earthquake. in 2008, and it created a large volume reservoir which threatened actually even some parts of Chengdu in Sichuan province, and therefore they tried everything here to breach this dam. You know, you don't really see it well, with some equipment which was flown in here by heavy helicopters, and they could create a breach which was then heavily eroded, but it was considered a big success because the flood which was created by this breach of this dam had approximately, was a flood with a return period of 250 years. But you know, for dams, for let me say flood safety of dams, you either look in 10,000 years return period, or embankment dams, you look in a so-called PMF. Okay, next. Okay, we have also plenty of rockfalls, as you can see here. This is in Switzerland. We have some nets for rockfall protection, or we have here, it is in Iran during construction. Okay, this person, just before I arrived, just this person passed away with this rock slide. Next one. Okay, we have a lot of, in a reservoir impounding, you get some stability issues, which is here, reservoir impounding shown in Iran. Next one. Okay, this I think somebody has shown also is a Vaillant Dam, is a famous failure of, let me say, of this slope here. Is a, you see this whole slope failed. There was one dam, arch dam. At that time it was the world's highest arch dam, 260 meters high. So this slope failed with 260 million cubic meters, and it basically displaced the whole reservoir, and the flood wave here overtopped this arch dam by more than 100 meters. But the dam, it is in a narrow canyon. When I visited this place here about 4 years ago, okay, you see here from this huge overtopping, we just have some local damage near the crest. The dam is still there, but it is not operated. It's about, in a downstream part, about 2,000 people were killed. It's the biggest disaster in Europe from dam construction. Next one. Okay, this is from Switzerland. This was also the world's highest arch dam at some time, 250 meters. But you see, we have also a lot of rock falls. Some rock penetrated or destroyed this retaining wall, fall on this abutment. And you see here some rocks falling from higher elevation, created quite some craters in the concrete. So you can say if you have an arch dam, I must say in Switzerland, because of military reason, such high arch dam must have a thickness of 15 meters. It's not a problem, but there have been arch dams built only with 2-3 meters. So if you have this kind of rockfall in thin arch dams, you have a safety problem also of this dam. Next one. Okay, now let me say a few words about earthquakes. Okay, earthquake, usually people look into ground shaking, but we also have some faulting. There are a number of faults, and this morning the chairman of WAPTA presented the Tarbela Dam, and actually the Tarbela Dam is also on faults. You know, these faults were detected basically or declared active after the dam was constructed. Okay, so we see if we have some dam on a fault, and if a fault is passing through this dam, like here in Taiwan, a Gigi earthquake, you cannot build concrete structures to resist fault movements. Next one. Okay, typical features of earthquakes in the epicentral region are the huge number of rockfalls. This is from the Wenchuan earthquake. Some people mentioned about 100,000 rockfalls, not only one. I think, like it was mentioned from Kenyir Dam in Malaysia. It is all is only rock falls. This is from Iran, 1990, just near the dam. Here is actually the intake of a spillway, so quite big boulders falling there. Next one. Okay, this is a dam damaged in Japan during the 2011 earthquake. Actually, it failed due to overtopping, and you can see here about 8 people were killed due to the failure of this dam. The water was released very fast, which has caused then a rapid drawdown failure of the reservoir flanks. It's quite unusual. Those who are doing a stability analysis, they look into the load case of rapid drawdown. So this is an accidental rapid drawdown, and you see here, this is not just at the dam, this is at the reservoir rim. So we have, due to rapid drawdown, we have this failure. Next one. Okay, now this is from India. You see one of the problem which is encountered if people are using the old-fashioned design method, which I wanted to mention, like here, even if an earthquake occurs, some damage occurs also according to the design method, no damage should have occurred. Okay, we see here some damage. So therefore, the old-fashioned, which you also, I'm sure, you also like to use here in Malaysia, does not really guarantee that your dam will not suffer any damage with that, using that old-fashioned concept. Next one. Okay, this is just to show the effect of a quality of dam construction. Finally, the behavior of the dams depend on the quality of your dam. And you see here, this is in Albania, in Europe. There was only a magnitude 4.1 earthquake. In Malaysia, you can have that everywhere, you know. So if you have a poor quality dam, you see you have a major slide here, and you have basically it's almost a failure. You see here the reservoir. So what I want to say is, if you have a poorly designed dam, even small events like the static liquefaction I have shown before, you know, could cause failure of these dams. So in your dams, you must be very sure to have really good quality construction. Next one. Okay, this is the opposite case in Japan. It's a good design. Here the peak acceleration was about more than 10 times higher than in the previous one. It was 1G. And basically this dam here, it's about a 74-meter high rockfill dam here. It only experienced a settlement of about 40 centimeters. So if you have a good design and good quality dam, this dam can survive very strong earthquakes. If the quality is poor, it will fail already under small earthquakes. So I would only like to emphasize, you should emphasize on good contractors doing a good job. Next one. Okay, this is an example in Iran. I have been involved with that. This was a big earthquake with, in 1990s. Also about 45,000 people were killed, similar to the number of people killed in a recent earthquake in Turkey. But what I want to say is, if an earthquake occurs, it is important, and this is just after the earthquake, that you can open the low-level outlets, or people call it bottom outlets. Some people call them flushing outlets or irrigation outlets. I call them low-level outlets. So it is very important, because this dam here was damaged. We see even there were all kinds of cracks. So to increase the safety of the dam, you opened these gates to lower the reservoir in the dam, and with that you can increase the safety of your dam. So I want to say here, also in Malaysia, to install low-level outlets is an important safety issue for your dam in a case you had some incident. Next one. Okay, we see here some damage in a concrete dam. There are some cases which are exposed. The next one, just to go. And of course, we have a lot of damage also on the buildings near the dam. We have the damage in switch yards, which is partly on excavation, partly on fill, and we know for seismic structures on fill are very sensitive. Next one. Okay, now what are the options for mitigation effects of natural hazards? I've just shown a few. First, we can design against these hazards. Number two, we can eliminate the effects of hazards, which is, for example, for powerhouse. If you have a rockfall hazard, you build an underground powerhouse, so therefore you eliminate that hazard. So there are some options how to do that. We can reduce the hazards by stabilizing, for example, some slopes. We can install early warning systems. We prepare emergency action plans, and we provide, this has also been presented already, water alarm systems for alarming the people. Next one. So let me say a few words about man-made hazards, if I just have 5 minutes left here. Man-made hazards, it was also mentioned, design errors, poor construction. I mentioned already, quality of construction is a key issue. Okay, we have faulty operation of equipment, we have sabotage, terrorism's act of wars. If you have that, basically you can only do a post-event evacuation, or if there are some threats, you may be able to do that. And there are some other hazards or unknown hazards. Let me say in the last 2-3 years, people talked about cyber criminality. These days now we see in Ukraine, people are doing a lot with drones, you know, so if we think terrorists, it becomes easy even. We think that terrorists get access to drones and to explosive, which could be transported to such sites. Next one. Just to show a few examples, this is a pump storage plant in the US. I think it is known. This is a concrete face rockfill dam, and it failed. As you can see here, it failed. This is the upper reservoir. It failed because they were pumping water in the upper reservoir, and the water gauge was not. The water gauge indicator was not working properly, and there were new staff, so they were pumping water not knowing that the reservoir was full, so it overtopped. So we can also say today, if you have upper reservoirs, also though inflow, you still need a spillway, and the spillway capacity must be equal to the pumping capacity, you know. So it is basically also a design error, and it was a faulty error in operating this plant. Next one. Okay, this is a new one on the right. It has been replaced by a CFRD dam, by an RCC dam. Okay, this is from Albania. This is from the operation of spillways. We have here maybe the hydraulics of a spillway was not yet looked carefully, so it eroded the toe, the downstream toe of it is actually a CFRD dam, but it is a toe. It is not. It doesn't look good, but some people think this is a safety issue. The dam will not collapse because of that. Next one. Okay, we have man-made. Man-made has a lot to do with maintenance. This is from the Philippines. Okay, in Malaysia it's the same. You have a lot of growth. In Switzerland, it would take 50 years that plants grow like that. In the Alps here, in Malaysia or in Philippines, it just takes a few weeks to grow like that. And there are some problems with corrosion protection, as you can see, because if your corrosion protection is deficient, the lifespan basically of these elements will decrease. Next one. Okay, this is again from Albania. We have some leakage. It's not directly a safety problem. In these penstocks, you see we have already a lot of corrosion, so it's better to do this protection before to expand the lifespan of these projects. Because today, let me say, if you have existing dams, the main concern is to extend the lifespan of your project as long as possible. Okay, next one. Okay, this is the dam which was also shown, is the Atatürk Dam, is the biggest dam in Turkey. We were actually even the designer at that time. And it was mentioned that this earthquake, which has occurred on 6th of February, the epicenter was about 120 kilometers from this dam and has a huge reservoir, the reservoir being much larger, probably even than all dams in Malaysia together. It's about 50 cubic kilometers. Okay, anyway, what I wanted to say here, okay, in Turkey, it was required to complete, because the president required the date of inauguration of his plant was fixed. So the contractor had to do the work too fast, and immediately after the inauguration, which could be held, there were quite major settlements of the dam, which required here, you can see here, the top 15 meters, the dam volume here is about 85 million cubic meters. It's just the number 2 or 3 after Tarbela, which was presented before. And you can see, because of the settlements, they had, just after completion of this project, they had to rebuild the top 15 meters of this dam. And you see this is this reconstruction which was going on. It was because the contractor was put on the pressure by the government to complete at this state, and then the quality of the work basically suffered. Next one. So it's a man-made. Okay, this is from Germany. These are basically masonry dams, stone masonry dams, and they were 2 of them. I think the German WAPTA has also shown one of them. Okay, there were 2. One is called Edertalsperre, and the other is Mönetalsperre here. So the British Air Force dropped some special designed bombs, about each one about 2.5 tons of explosives, which traveled on the water here to the dam face, and where it fell about 20 meters, and it exploded when in a water, which created this breach of the dam, of these 2 dams, and a large number of people were killed due to these events. So these are man-made events, you know. Next one. You may also have heard now in Ukraine, you know, it is claimed there are a number of run-of-river power plants. It is unclear if the Russians have caused some damage or did some operation, or if the Ukrainians have done it. Okay, this is a project I was also in charge. This is right at the border of Switzerland to Italy. And in the 1970s, there was a lot of terrorism from Italy, so-called Red Brigades, and they threatened that dam. Okay, I'm not showing the dam, it's a 130 meters high arch dam, but if you have a massive dam, you cannot just threaten it, but you can threaten the weak elements. These are with spillway gates, so I'm not sure if you can see here. So there is, as a protection, because here is a road about, let me say, 7 meters away, so you could throw some explosives basically to these gates, and to protect these gates, these high-strength nets were provided with nets were removed about 4 years ago. Okay, now we don't think, but we have them for 30 years. Next one, I want to finish here. Just this is from a former Soviet Union or from Russia. This is Sayana Shushenskaya. This is the largest dam in Russia, is in Siberia. Okay, this is a picture I've taken there once. Okay, next one. Now, there was some problem. You see, it has about 6,000 megawatt. This is one of the biggest power plants in Russia. And due to the operation of the turbines of a power plant, there was some fatigue failure of bolts here. And then, due to internal pressure, it exploded basically, and you see it destroyed from its 10 units. It destroyed 9 of them. It destroyed basically the whole power plant. You see, a powerhouse, due to fatigue failure of bolts of its turbines. Took then about 5-6 years to replace them, and during that time, the water had to be released by the spillway. The spillways are also not designed for this long-term operation. There are here in this area, I think they also had minimum temperatures of -50. Okay, maybe every 10 years. It was pretty cold. Okay, so a lot of ice created also in a spillway. They used the spillway operation. Okay, next one. I have to finish now. What are the options for mitigation? For quality, we do independent checks, quality control of construction, operation and maintenance by qualified personnel, control of access of people, okay, that is for terrorism and so on, emergency action plans for all types of hazards, preparedness against fire and hazardous substances, protections against cyber criminality, procedures and plans for lowering the reservoir. But I would just like to mention, okay, people talk a lot on risk-informed system and so on, but if we have basically with man-made events, probabilistic safety and risk analysis are basically not suitable in a case of man-made hazards, because there is no frequency analysis, and there are some other peoples who control when such actions occur. So if you do safety analysis, I must say in Switzerland, we have a few nuclear power plants, and the safety of nuclear power plants is on a probabilistic safety analysis. You could say it's risk-based, but they do not consider these risks because it doesn't fit, that is what I say. It doesn't fit in their format of probabilistic risk. So these biggest risks like terrorism, acts of war are basically not considered, but they are the most frequent one. Okay, next, just to come to the conclusion. Next, please. Okay, when there are some project-specific hazards, next one. I just want to mention here is a Mosul Dam, which was in Iraq, which once was considered the most hazardous project. The problem here was basically seepage, because the foundation is of gypsum anhydride, which dissolves. So if it would be uncontrolled, it would create large cavities under this dam, which is by far the largest dam. If it would fail, about 300,000-400,000 people would be killed along the Tigris River down to Baghdad. Okay, this is from Thailand. I have taken also about 3 years ago. This is a kind of internal erosion. It's just a small reservoir which caused a breach, and it caused here already some piping. It is quite interesting. And to come to the last one. Next, next one. Okay, to conclusions. What I want to say, large dam projects may be subjected to a large number of hazards, not just the natural hazard, not just flood and earthquakes. But most people doing safety analysis are basically focusing only on those. But I hope I have given you a broader view of the hazards which are applicable. The hazards are natural hazards, man-made hazards, site-specific and project-specific hazards. And there are new hazards which are emerged, and those new hazards are man-made hazards. Okay, and most hazards, I would like to say, which I have shown, are time-dependent. Not only the climate change hazards, so the dam engineers actually have known how to deal with time-dependent hazards, and I would say they also know how to deal, those who are concerned with dam safety, they also know how to deal with climate change hazards. It's not different from what we have the others, and the answer is basically you have to do periodic safety reviews, you have to do basically not to do a prediction in 100 or 200 years, but you have to follow a participatory approach by looking into the safety at intervals as you are doing, let me say, every 5 years, and at that time you will see if some action will be required. So thank you very much, and I've taken more of time. Some people were also coming later. Yeah, okay, that is basically a question of tailings dams. Okay, so I must say, it was mentioned in a presentation yesterday, and that is what we, of course, are saying already for a long time. Tailings dams must have the same safety as water dams. Okay, because the tailings dams, if it is full, it is there for hundreds of years. So therefore, let me say, even the seismic hazard there, which have to be taken into account, is even should be stricter than that for water dams. But it is basically the opposite the case still, because in mining, the mining companies, their core business is not dam construction. They want to extract some metals or whatever it is. So, but I was involved in one in tailings dams in former Eastern Germany, where the Soviets extracted uranium. Okay, so there are these tailings dams, but these tailings dams are put in they have to be put in a stable condition, and you have to check to protect that your rainfall or inflow do not dissolve the hazardous material in these tailings. But this is a separate issue. But the one which I showed very quickly in a Mosul dam, it is basically a chemical dissolution in a foundation. This gypsum is dissolved, and when it creates big cavities, and therefore there is, let me say, 24 hours per day and 7 days, 365 days a year, people are grouting. So for the whole lifespan in this Mosul dam, people have to do grouting to keep it.
Thank you so much, Dr. Wayland, I was fascinated by the range that we were able to see during this presentation and the kind of unorthodox hazards that engineers probably don't learn to address in the course of their day-to-day work. But it was a bit sobering as well, in the sense that we're so used to looking at design and engineering solutions to mitigating some of these hazards, but there's a very sobering realization that there's more going on. And the fact that man-made, of course, but then the more perhaps currently relevant things like sabotage and so on become the preserve of engineers. So I think that's something that some of us will be thinking about as we return and see how we can put engineering solutions to work to non-engineering causes. Well, today's session has been great, and also it's I've done a few chairings before, as you might imagine, but I've never simultaneously moderated two sessions that appear in two different parts of the brochure. So even I was a little confused about how to get my head around that one. But thanks to the wonderful support that I have from the staff here, I was able to, well, I imagine I was able to synchronize them. So we're now coming back to the oral presentations after this wonderful interlude. And I have one paper to announce, which is in the theme of hydrology, hydraulic and environmental engineering. And the paper is titled Sedimentations at Intakes and Water Conveyance Tunnel for Hydropower Schemes in the Lower Pia Hydroelectric Scheme. The authors are Lewis and Othman. So if I may invite the presenter to the stage, and we are now resuming the oral presentations, ladies and gentlemen. These are 10-minute presentations, and since we've been very generous with allowing time beyond allocations, this time you'll see me a little bit more ruthless. So please forgive me in advance if I literally push you off the stage at 10 minutes. But I'm sure we're going to enjoy these 10 minutes as well. Thank you.
Thank you, Chairman. Can I have my slide? Yeah, this is the one. Very good morning. Yesterday we heard a lot of talks on ICOL main concern areas, and sedimentation is one of it. I've presented a few topics on reservoir sedimentation, so now I'm going to talk a little bit about tunnels, which are used to convey these to powerhouses. I'll be touching on Lower Pia as an example. Next. So as a brief content, I have about 6 areas to cover. Since I have only 10 minutes, so I'll be going a little bit fast. If you have any other questions, maybe after the sessions, you can always meet me and we can discuss. Next. So importance of hydropower, these past 2 days we've been talking about it in terms of energy security, in terms of storage and all that important. So TMB, we do have a lot of plans for upgrading our power plants and so on, and it is one of in our ESG initiative for green energy. Next. Okay, so these are where the plants are situated. We are building one new one, which is Ningiri, and the others are all situated in the central and northern region. Next. So there are a few types of hydropowers. So we did talk about storage. So this Pia, I'll be talking about runoff river. And of course, pump storage, we have plans for that, but we really don't have one yet, but there are some studies ongoing. Next. So the main components of the hydropower scheme involves weir, intake, tunnel, headrace, powerhouse, and all sort of components. So this layout on the right is for Sungai Pia, for the lower underground scheme. Next.
Okay, next. So, Dr. Roslan presented also. The oldest scheme is actually Chandro, but apart from that, we also have Cameron, and Pia is about 31 years old. So it's also equally old. Next. This is the whole network of how the interconnection of Pia looks like. So it's all connecting the various rivers into two powerhouses. One is the upper and one is the lower. So the upper powerhouse is above ground and the lower is underground. Next. Okay, so we'll be touching on the lower scheme. Next. So this section of the tunnel, which is about 12.5 kilometers long, consists of the tunnel network from the upper powerhouse right up to the lower powerhouse and the terrace section. So during our routine inspection, we do inspect these tunnels to see their conditions and so on. Okay, next. So I'll be touching two of the intakes under this scheme and their conditions. Next. Next. So intake and tunnels, they are basically interconnected. The intake is actually to divert the water into the tunnel system and then to the powerhouse. So they have main function not only to draw water, but they also are designed to eliminate to a certain degree debris and sediments. Okay, next. So by design, there are two types of design for the intake. One is, we call that a lateral intake structure, which most of the larger intakes will look like this. They will involve inlet, trash crane, spillway, settling basin, and so forth. Okay, next. This is an example of a lateral intake design, which is at Pergao. This is a Terang intake pump station. Next. So these are all the lateral slots that goes into the power system. Next. While the vertical inlet structure, it also has a typical weir that diverts the water, but here the water enters through the intake structure through a series of vertically installed trash cranes, like you see there, and then it goes into the tunnel system. So water drops more of a vertical motion. Next. This is an example of shear intake. So water is being passed through the inlet. Next. There is another type of vertical system, which is at Cameron Highland, at Woe intake. Okay, next. So there are quite a number of reasons which one we would select, whether it's lateral or bottom intake. But by experience, we noticed that most of the larger scheme will be bilateral, and then most of the smaller rivers, we would use the vertical intake. Next. This is an example in Austria. So this is a full inlet that's placed on the weir. So ours is slightly different than this design. Next. So Lower Pia has 5 intakes. These are all the dimensions, and they also have other structures like diversion and also outfall. Next. So proper design is important for water as well as prevention of sediment and debris, as we saw. So we will look into the other part. Next. Okay, so 2 case studies. So this is Sule. Okay. So when we inspected this structure, we were hoping to see a lot of structural damages, but we also found that other things that are there inside the tunnel, which also requires attention. Next. This is the layout, which is more of a lateral design. Next. So it's one of the second largest intake, which draws water from the Pia River. So it's about 18% of the total flow. Next. Okay, so it has a lot of features. It has a weir, it has an intake chamber, it has a descender, and also flushing conduit. So basically, when the design, this was in 1980, so when the design has included descender, then there is a design assumption that sediment will enter this intake and it has to be mitigated, so the design is there. All right, next. Okay, this is the descender. It's a single section descender. Next. So when we entered, we do notice a lot of debris at the intake and also at the trash screen. Next. The flushing tunnel is used regularly to flush, and that's why the descender is empty. So periodically, sediment are being removed from the descender. Next. So we also inspect the shaft. So normally we do this by abseiling from top to bottom. So this is about 30 over meter. So we do that. Next. So when we drop down to inspect the bottom part, we notice that this section of the diversion edit between the intake and the main tunnel, we noticed that it was quite full with sediment. Okay, so that did not allow us to enter because the mud there is a little bit soft, and it's almost about 10 meter in length, so almost blocking the entire opening of Sule. Next. So this is the view of the sediment that we noticed from inside the tunnel. So that makes us to wonder that the descender, the capability of the descender, and also why did so much sediment enter into the main tunnel from the intake. Next. So findings, the pond itself has almost quite a large amount of sediment at the intake area, and mostly consisting of sand, silt, and clay. Okay, next. So inside the tunnel, we notice that the edit is almost 50% blocked, and while the sediments volumes are not so big, but once it's completely blocked, then we will have a backwater effect. So you don't get a full efficient tunnel system that's going through the hydropower scheme. Next. Here, next. So this is the layout drawing. Okay, next. Okay. Yeah, so again, next. Okay, this is the upstream. It's a very small stream, single stream. Next. So we went down. Next. So also same. You notice that there's a lot of sediment inside the tunnel section. Next. So here we try to go in to see how far we can go in. This engineer is seated there. You can go and see him, ask him his experience. 30-meter length, full section is covered almost about 70-80% of the entire tunnel system, blocking the whole section of the inlet. Next. Okay, so, okay, next. All right, inside the tunnel sections also, we notice there are a lot of significant amount of sediment. Next. Findings, next. So by estimation, we noticed that the design period, the sediment volume is roughly around 5,000 meter cube a year, but today we are looking at 10 times more. Okay, so when it's 10 times more, definitely everything will start to choke. More frequent maintenance have to be required, more cleaning have to be required, more inspection have to identify how we are going to address this issue, because it also provides inefficiency to the hydro plant itself. So this is a ever-going battle that we address. Next. So some clearing work, periodic clearing work at the intakes and so on, we do carry out that mechanical excavation and so on. Next. Okay, next. This is at Chair, so people manually, because it's a very small area, you cannot bring excavator and so on, we got to do it manually. Okay, next. Conclusion. Okay, so the design caters for older design. So nowadays, more land clearing and so on, so we need to relook back at the configuration as well as the design requirement. Maybe we might need more descenders or more frequent maintenance, but these are some of the issues that we are addressing for our hydro intake. Next. Okay, so monitoring is still ongoing, and we also try to improve every time we see situation. Okay, next. Okay, thank you. This is the end of my presentation. I hope that was 10 minutes.
We're doing excellently, much better for time than before.
Okay.
We have time for one question, if anybody would like to ask. Great. Well, thank you, Dr. Canselor. It's very kind. Thank you for being prompt and crisp. Well, now the program, as you know, is a little bit dynamic as we speak. So I've got instructions that we've got about 30 minutes to wind this up. Today is Friday, and some of the audience would like to prepare for prayer. And so we need to wind up in 30 minutes. So what I have in mind is to ask if any of the presenters, the oral presenters, are here at the moment, and then we can take 10 minutes each for you. And so if you are here and you were planning to present, please let us know. So let's do that quickly. There is one presentation, 2 presentations, 3. Well, yeah, that's about half an hour. So the request is to please walk up, let me know who you are, and then we'll introduce you, and then 10 minutes in, you'd like to bring the other people on. Is that a good way to conclude this? Okay? Right, so the first hand that went up was here. Yes, please. Would you like to come over and make your presentation? Please join us. Please. And if you don't mind introducing yourself and your topic, since we've not met.
Thank you. Paper ID 031. Yes. Thank you, one and all. My paper title is Integrated Approach of Dam Break Analysis and Flood Inundation Mapping using HACRUS, a case study of Ukai Dam, India. My name is Dr. Ezaz Pathan, and I am a senior research fellow at Indian Institute of Technology, Gandhinagar, Gujarat, India. Let's start. These are my content: introduction, objectives, study area and data collection, methodology, results and discussion, concluding remark, and references. Now, dams are prevalent water holding structures that are built to store for water for irrigations, domestic uses, flood mitigations, generation of power plants. And beside this, if it fails, so we can see causing significant property damage, losses of life, etc. India has made significant investment in dam and related infrastructure. You can see we have third rank after US and China in context of large dams. We have 5 large dams and 447 are under construction. So this figure is expected to rise in upcoming years. So between 1960 and 2010, there were 23 major dam failures in country as reported by dam safety organizations. Next. So, for consequences, the dam break simulation and subsequent flood simulation are critical and crucial for identifying the mitigation potential dam failure threats. Over past few years, HACRUS, Hydrologic Engineering Center River Energy Systems, has become the most frequent used software for dam failure studies. It is open source. Guys, I'm talking about my study is based on only open source data sets. In the scarcity of data, we can use open source data sets. Our data is based on geospatial techniques. So many researchers have simulated model based on HACRUS dam break analysis. Next. Yes, objective of my study is to perform dam break analysis of Ukai Dam using 2D HACRUS model, to prepare flood inundation maps in terms of water depth, velocity, water surface elevation, and arrival times, and to predict dam break flood magnitudes and generate break hydrograph. These are 3 objectives I'm going to present. Next. This is my study area. You can see is India, the lower Tapi River, and is Ukai Dam. Here the Ukai Dam, my study is Surat city, which is located 100 kilometers downstream of Ukai Dam and 19.4 kilometers upstream of mouth of River Tapi. These are lat long of my study area. Next. Yes, you can see in the figure, this is Ukai Dam. Yes, This is Surat city, okay? And the colorful image you can see, these are the 7 zones. It is divided into 7 zones. So I will show you the inundation and consequences of flood, dam break in this my study area. Next. Yes, this is the characteristics of the Aqua Dam, reservoir characteristics and spillway. Next. Yes, these are the data I have gone through. SRTM data. I told you earlier, I'm using this dam break analysis for open source. We have used 30 by 30 resolution DM, okay? And this is the source of website, USGS. Projection file I have directly downloaded from the spatial references. Land cover map I have obtained through MODIS land cover. Inflow and discharge data of Aqua Dam 2006 flood hydrograph. Hourly inflow and discharge. Next. I think I updated my PPT, it's earlier. Please open that PPT, it's important. Yes, this one. Sorry. Yes, directly data collection part, yes. Thank you. Yes, these are the methodology. Some of students are for, I think, or the researchers. You can see this is a flowchart of my methodology. First, a literature review and data collection, then estimating dam break parameters, then HACRES 2D hydrodynamic modeling, in which we have generated terrain profile, assigned roughness coefficient to the different LULC. Geometric data, and we have provided 2D flow hydrograph, storage area, connection, with dam, computation mesh, and boundary condition. Then, we have simulated unsteady flow, in which we have provided lateral inflow hydrograph as upstream and normal depth as a downstream. Now, dam break mechanism and running the simulation of model. And we will organize and we will visualize the results in the RAS Mapper, which is a GIS tool, open source. We can see the result based on the Google Earth, okay? In the form of flood depth, velocity, water surface elevation, and arrival time. Next. In model, if we will not look into equations, that it is nothing but input and output. So HACRES is based on Saint-Venant equation. These are the equations which is running behind the model. Next. And these are the time step is very important part for the simulation. These are the time step, current number we have used. Next. These are the dam break parameters. You can see average break width, break formation time, top and bottom width. These are the calculation. Next. Yes, you can see this is the Aqua Dam, and this is a 2D flow area. In between, this is dam assigned, this is dam, Aqua Dam, right? So, and this is the storage area, and this is our 2D flow area. Next. These are the LULC. I have used this MCDQ Q1 value with respect to Mannings. It is very important. Soil characteristics. Next. Now, this is 2D area connection and dam break parameters. These are the value I have calculated from the dam break parameters and incorporated in the HACRES. Next. These are the inflow hydrograph as an upstream boundary condition and slope as a downstream boundary condition. Next. You can see now results. These are the inflow at the dam, and this is a downstream hydrograph. Next. Yes, you can see the results of HACRES in the context of arrival time. You can see if dam break for the 2006 flood, you can see here is a 5-hour interval. What is the flood inundation map? 10 hour, 15 hour, 20 hour, and 25 hours. So it is very important for decision maker to take decision what should be the scenario of flood inundation. It is very important for to send the message to the authorities for prior evacuation. Next. Yes, this is my Surat city. This is a Surat city, okay? I have divided into different zone with E1, E2 up to E7. So you can see the maximum depth is observed at north and east zone, which is range between 10 to 19 meter. Next. This is flood velocity. You can see the velocity also I have marked, and we can see up to Kadod area, it is 4 to 6 meter per second, quite high. But in our city area, it should be lies between 1 to 2 meter per second. Next. This is water surface. SAM, the downstream of the dam is 80 meter up to Kadot 42, and downstream field it's 8 to 9 meter. Next. Now this is the arrival time map. We can also prepare the arrival time map using HACRS. You can see here arrival time is 10 to 13 hours. Means if dam break, it needs 10 to 13 hours to inundate the Surat city. Next. This is the summary of table. Distance from the dam in kilometer, maximum flood depth with respect to this area, flood velocity, water surface elevation, and arrival time. Next. Yes, summary of simulated results. From the analysis, we can see north and west zone of the Surat city are found significantly affected by the dam break, and the flood wave may cause severe damages to the study area. Water reaches the river in the channel Surat city within 10 to 13 hours from the Ukai Dam after dam break. The east 13 hour, west 14 hour, the north 14 hours zone were the first to get inundated, and followed by southeast, central, and south zone. And lastly, south-west zone is inundated in 17-hour arrival time. Next. The depth of flood water is found to be the maximum in north zone, 8.72 meter, east 7.56 meter, and west 6.28 meter. These are the statistics. And SAM velocities lies between 2.5 to 4 meter per second, and study area, it lies between 1 to 2 meter per second. Next. Now, we should know the limitation of the model and future scope. The limitation of the model is as the simulations are quite sensitive towards the DEM resolution. So hydrodynamic modeling can give more precise results with high resolution DM, means 1 to 5 meter in city level, because I have done on the 30 meter DM, so it is my limitation of the study. The more simulation data is required to improve the accuracy assessment and validation part. The model is simulated with the cell size of 140 by 140 meter, you can see. Due to unsupported computational hydraulic table with smaller cell size with the large 2D area, its limitation. Next, the future scope, yes. The future scope is concentrated with the non-structural flood mitigation method framework of machine learning and MCDM techniques, and by providing levees and flood wall by the structural measures. The real-time flood mitigation strategies might be developed by analyzing the model with regards to the flood, defense, and river training works. Next. Now the conclusion is, next, we can see as per the discharge, the city area or north and west roads are very high, vulnerable to the floods. Next, it takes 10 to 13 hours to reach the city full inundated. So immediate structural flood retention structure like levees, retaining wall are recommended at flood affected zones. Moreover, the non-structural system can also help the disaster authorities for prior evacuation and decision-taking system. Next. Next. Thank you very much. I would like to show a small video of dam break analysis, sir. If you have, I think.
And the video showing is at 4:30 today in the big movie theater.
Sir, only.
How long is the video?
Not more than 20 seconds.
Shall we take extra time if everybody likes? Because you know why? This is somebody else's time.
Yeah.
So if you allow, we'll let Dr. Patan.
Please allow. It's a 10 seconds video. You can see how dam break and how your study area will inundate. Yes, please see. Please pause for a half second. See, this is the reservoir area and this is a dam. Now, if in inflow hydrograph we will provide, then you can see the scenario how it dam break and how this Surat is inundated. Let's start. This is the scenario. And this is Google base map. This is the beauty of HACRA's open source model for flood inundation mapping. Thank you very much.
Thank you so much.
Thank you, sir.
Thank you for making time and thank you for being almost on time. Thank you so much. Right, we have 2 more hands up, right? So would you, whoever wants to walk up to the stage first is welcome. Yes, please, come along. And if you'd like to introduce yourself first and read out the title of your paper so the slides can be put up. Welcome. So I'm going to be as ruthless as I was.
Yeah. Got it. Thank you, Dr. Shah. My paper ID is 066. Thank you, MYCOLD, for inviting us. Today I'll be talking about the sustainable sediment management in a peaking hydropower project. It is a case study that we did in Kimathangka Arun hydroelectric project in Nepal. Let me start. So I've arranged my contents like I'll be talking about the necessity of sediment management and what we have done in Kimathangka Arun project, about our project details, and then I'll be talking about the objectives, data availability, and during discussion of flushing considerations, I'll be talking about the methodology as well. Then I'll conclude with the results and conclusions. Thank you. Need not mention much about the necessity of sediment management in reservoirs. As the dam is constructed, it accumulates sediment and it has to be managed. And the 20th century basically was more focused in designing and constructing new dams, but 21st century should be more focused in sediment management methods. Nepal is located in the Himalayan region and it has a very fragile geology. It has a harsh climate and sparse vegetation. Moreover, it also has tectonic activities. That's why it is more prone to sediment susceptibility. So sediment study is a must in our projects. Dr. Martin also showed a photo of the case in a mountain region. Talking about the methods that we could adopt, there could be a proactive method and adaptive methods. Proactive method is related more with the catchment management itself, whereas adaptive methods are more concentrated with sediment routing and sediment removal approaches. I'll be talking about flushing approach that we have adopted, and it is a adaptive method that we have adopted. Thank you. It is a 450 megawatt peaking project located in the northeastern boundary of Nepal. It is a transboundary catchment. Almost 99% of the catchment falls in Tibet, and which is a rain saddle zone actually. But in the Nepalese side, we have a very heavy rainfall. The catchment area of this project is around 24,000 square kilometer, which is a really big catchment if you talk about the catchments in Nepal. The project is located in the Arun River, and it originates from the Sizavangma mountain in Tibet. Thank you. I have demonstrated a layout of the headworks arrangement that has been provided for the project, and a cross-section details of the spillway arrangement and overall dam structures. This project was studied for various peaking hours, ranging from 4 to 6. So this is the demonstration that I'm going to do today is for the least peaking hour, that is 4 hours. By shifting the location of the dam, we are looking for various options. The current demonstration shows the reservoir of 1.6 kilometer and total volume of 3 MCM. This is the total height of the dam is more over 100 meters, but above ground it is 47.5 meters, and it has a live storage of 2 MCM. We have you can see the coffer dams, upstream coffer dam, downstream coffer dam, the main dam structure, the diversion tunnel structure, and then the bypass arrangement that we have done with that we have designed to bypass the flow out of the system. We have provided 3 sluice spillways, 2 breastwall spillways, and 1 overflow spillway for regulating the discharge and PMF. Thank you. Talking about the objectives, I'll be talking about the sediment management from the sediment management perspective. We have considered 2 sustainability in terms of peaking operation, sustainability in terms of sediment flushing, and the other objective is to verify the adequacy of the design low-level outlets to evacuate the sediment. Moreover, the head pond that has been conceived in between the intake of the bypass and the dam, it has to be able to settle the sediment particles both in monsoon and dry season so as to omit the construction of descender basins. And at the end, I'll be talking about the proposed integrated reservoir regulation and sediment flushing operation rule that we conceived. Thank you. Talking about the data availability, we did the topographical survey and we have the topographical features. You can see the relation of the reservoir volume and the surface area. I have demonstrated the data on the right. And about the hydrological data, we have the Uwagaon station, which is the most prominent station that could be used for this project because of its proximity to the project. We have 25 years of data from 1985 to 2010. For generating the daily hydrograph of the headworks area, we did a SWOT modeling, and these are the data sets, average mean monthly data sets that I have presented. Bed load has not been measured as of now, and it has been considered as 25% compared to, in addition to the suspended sediment load measurement. Suspended sediment loads were measured from 2018 January, and it has been continued, but during this study, we had data till October 2019 only. So this study is based on this time frame only. Thank you. In order not to overestimate the sediment load in the monsoon and underestimate the sediment load during the dry season, instead of creating a single rating curve, we have decided to split the rating curves below 200 meter cube per second discharge and above 200 meter cube per second discharge. That way we have established two rating curves for this, so as to go more towards reality. We have been conducting various sediment PSD data. I have demonstrated few only. You can see the variability of the sediment. Like let's compare September 2009 with the 302 meter cube per second discharge, and it is comparable discharge in 311 in 19th of June. And if you see the plots, the blue line and the another one, you can see that the rating curves, the percentage finder curves, the PSD changes quite often, which is very obvious in Himalayan rivers. We have developed two suspended sediment rating curves for this project. Thank you. Here I want to demonstrate how the suspended sediment and the discharge variability affects month-wise. Like you can see that in the dry month, on both ways, even the discharge and the sediments are less, but in the monsoon, we can see the peaks. I have demonstrated suspended sediment and the total loads and the discharge as well in the monthly basis. Moreover, in this chart, no matter we have tremendous amount percentage of discharges below 100 meter cube per second discharge, but discharge above 300 up to 700, it contributes much to the sediment into the reservoir. That's why it gave an idea for us that we have to flush the system only after 300 meter cube per second discharge, so as to maintain the trade-off between the energy generation and the sediment flushing, and for the sustainability of the reservoir. Thank you. This is the kind of strategy that we have adopted for reservoir. Sorry, back. Yeah. In the dry season, we'll be operating at the full supply level, and also in the monsoon season, we'll be operating at the full supply level, but we'll have flushing events eventually, flushing events in the monsoon. The whole concept is that most of the design discharge is 150 meter cube per second only, 145 plus 5 is the environmental release. So we'll be bypassing rest of the flow from the bypass tunnel, and then in the head pond area or the descender area, we'll be inputting, only the design discharge will be entering. That way, the discharge in the head pond will be reduced, and it will have a more effective descending phenomenon over here, and most of the flow will be bypassed through the bypass tunnel. So talking about the SRS model, it is a one-dimensional mobile bed model. And for talking about the inputs, we have the inflow to the reservoir as the input. Water level at the dam is also an input. Sediment loads, longitudinal and cross-section details, sediment particle characteristics, and the measured temperatures are the inputs. There are 6 inputs. Moreover, talking about the boundary condition, daily hydrograph will be used as the upstream boundary condition, reservoir water level considering the flushing as the downstream boundary condition, lateral flow using bypass tunnel as the intermediate boundary condition, and sediment inflow boundary conditions. This is how a conceptual model developed in the Excel would look like first of all, we prepare this conceptual model in the Excel, and we give this input into the HRS1D to see the validation. Thank you. We cannot trust the results of any model without doing the calibrations and other checks, right? So since this is a project under construction, we do not have data to validate this model. So at least what we could do is that we could see that whether the sediment volume deposition in the model is stagnant or not. After certain years, there has to be a trade-off, and it has to be like all the deposition has to be washed away, and then the volume has to be maintained. So after 2 years, you can see that the volume is almost maintained. There are some depositions as well as there are some erosions, and then volume is always almost maintained. You can see. I'm almost done, sir. Oh my God. Yeah. Sorry. This is the elevation profile that I have presented in a 5 years basis. This shows that most of the sediment will be accumulated in the entrance region, and however they get washed away eventually. Yeah, we could go to the next one. This is how the cross sections would look like, and eventually the blue one is the live storage volume, which was maintained initially, and at the end of 25 years of simulation, the red one is the volume that has been, like the shadowed portion is the volume that has been lost. So the 4 hours peaking will be lost to 3.7 hours at the end of 25 years. Yeah. I already mentioned about the head ponds performance as a descender. So I have simulated 2 scenarios. This is just after the flush. This is the good scenario, and the line one is the worst scenario. This is just before the flush, means just even like tomorrow, if tomorrow you are flushing, then today is the worst time for the sediment to settle, right? So we can see that almost in both cases, the fine sediment and very fine sediment, fine sand and very fine sands will not get into the intakes, both in wet season and dry season. Thank you.
Been a wonderful session. Thank you very much.
Yeah.
And if you would all kindly take a look at your programs. 12:25 is the cutoff time. You don't have to go. I have to still thank you. It's the cutoff time, and I've just received a message that transport is leaving for Jummah prayers. So those of you who would like to make preparations for your Jummah prayer, it's my job to also inform that people that want to leave now may wish to do so, can do. And I'd like to thank you. Sorry, I didn't want to interrupt you. This is a lot of hard work, I understand. And this is a lot of very, very useful information. I also understand that. But there are certain things we can't move, like the Friday prayer. So please forgive us for cutting this abruptly. I can leave, but if you like, we can finish this slideshow. And those of us that want to stay can. Is that okay? But you would have to forgive me because I have to make that bus now and get out of here, right? So my thanks to you for your patience. This has been a very dynamic session. We've had to move around a little bit, but it's also been a very useful session. So if you would like the speaker to continue, I've requested him to stay on and finish their slides, and I'll ask to be allowed to leave. Is that okay? Please come back if you like. So thank you, ladies and gentlemen. It's time for me, and it's been a pleasure and very unusual chairing this session, but I've enjoyed it as well. Thanks a lot.